Humans have wondered the ideas of life and the universe for thousands of years. We, as a species, have been aware of space for as long as we have been able to look up at the night sky. One of the first notable ideas about the universe dates back to ancient Greece around 600 BCE and to Hindu scriptures like the Bhagavata Purana and the Bhagavad Gita. In modern times, Newton and Einstein have also made significant contributions. Today's narrative will include some interesting mysteries of the universe. We will start with our own solar system to alien worlds, and then move forward on cosmology. Like the formation of the Moon, the Earth's magnetic field, and what it does for us, how it creates the northern lights, and going all the way back to the start of the universe, the Big Bang. So what is the evidence for the Big Bang? What was it? When did it happen? But most crucially, how do we know? These are difficult questions to answer. The Moon is one of the largest objects in our solar system, almost as big as Mercury and significantly larger compared to Earth. This size similarity raises an interesting question. How did Earth and the Moon form to be like this? Why are these two bodies orbiting each other? There are also some intriguing facts about Earth and the Moon. For instance, this beautiful picture taken by a space probe orbiting Mars a few years ago shows Earth and the Moon from Mars' perspective. One fascinating fact about the Moon is that it has very little iron in its core, unlike Earth, which has a lot of iron in its core responsible for its magnetic field. This difference is puzzling because if the Moon formed in the same region as Earth, why does Earth have so much iron in its core while the Moon has so little? Another interesting aspect is the amount of spin in the Earth-Moon system. The Moon is quite large compared to Earth, orbits it quickly, and both Earth and the Moon rotate. A fundamental principle in physics is that spin, or angular momentum, doesn't just appear out of nowhere. It must come from somewhere. So when you see the Earth and Moon spinning rapidly and the Moon orbiting Earth swiftly, there must be an explanation for that. Why is there so much angular momentum and spin in the Earth-Moon system? One of the greatest achievements in human history was when we landed there in 1969. During this mission, we collected moon rocks and brought them back to Earth. Scientists found that the composition of these moon rocks is very similar to rocks on Earth. This suggests that the Moon and Earth might have come from the same source. By examining the decay of radioactive elements in the moon rocks, we can determine their age. These rocks seem to be about 30 to 50 million years younger than Earth. While this difference might not seem significant, since Earth is about 4.5 billion years old, it does indicate that the Moon formed slightly after Earth. Another interesting fact involves isotopes, which are different forms of the same element. For example, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. The same concept applies to oxygen. The ratio of these different forms of oxygen can be measured very accurately. In various parts of the solar system, these ratios differ depending on how close or far a planet formed from the Sun. However, on Earth and the Moon, these ratios are very similar, indicating a shared origin. So we have a bit of a question here. The Moon is slightly younger than Earth, spins quickly, is made of similar materials, but has very little iron. What's the explanation for that? There is a widely accepted theory that explains all these things. Some people question it, which shows how science works. It's not 100% correct or accepted, but it makes sense based on the evidence. Scientists have several theories about how the Earth and Moon formed. One of the most widely accepted theories is the giant impact hypothesis. The theory suggests that about 50 million years after Earth formed, another planet, about the size of Mars, was very close to Earth. This planet hit Earth in a glancing blow, knocking off a lot of debris without hitting the Earth's core. When planets form, heavy elements like iron sink to the center. So when this collision happened, the material knocked off had little iron because most of the iron was already in Earth's core. This collision also caused a lot of spin, similar to kicking a football on the side to make it spin and curve. This explains why the Earth-Moon system has so much spin. The Moon is made from the debris of this collision, which is why it has similar materials and isotopes as Earth. Since the collision happened 50 million years after Earth formed, it explains why the Moon's rocks are slightly younger than Earth's. It seems the Moon formed from a planetary collision about 4.5 billion years ago. All the evidence supports this idea because of these 4 observations about the Earth and Moon. Plus, we went to the Moon, collected samples, and analyzed them in the lab, which backs up the theory even more. Another interesting point is that this collision not only formed the Moon, but also played a significant role in shaping Earth's future. The impact likely tilted Earth's axis, which is why we have seasons. Without this tilt, our planet might not have the same climate patterns that support diverse forms of life. The presence of the Moon also helps stabilize Earth's rotation, preventing extreme shifts in its tilt over long periods, which would have drastic effects on our environment. Moreover, the gravitational interaction between Earth and the Moon creates tides, which have influenced the evolution of life on Earth. The regular rise and fall of ocean levels have impacted coastal ecosystems and human activities for thousands of years. Moreover, the Moon is gradually moving away from Earth. Measurements show that the Moon drifts about 3.8 centimeters farther from Earth each year. This slow separation affects the Earth's rotation and the length of our days. Millions of years ago, days were shorter, and as the Moon continues to move away, days on Earth will gradually become longer. While the giant impact hypothesis is the most widely accepted theory, several other fascinating theories exist. One such theory is the fission theory, which suggests that the Moon was once part of the Earth but separated due to the planet's rapid rotation in its early days. This rapid spinning caused a chunk of Earth's material to break away, eventually forming the Moon. However, this theory struggles to explain the Moon's current orbit and the mechanics of such a separation. Another interesting theory is the capture theory. According to this idea, the Moon formed elsewhere in the solar system and was later captured by Earth's gravitational pull. This could explain why the Moon has a different composition from Earth. However, capturing such a large body without it breaking apart seems highly unlikely. Despite these theories, the exact process of the Moon's formation continues to be a topic of scientific investigation and debate. The unique relationship between Earth and the Moon also has a significant impact on life here. The Moon's gravitational pull creates tides, which have influenced the evolution of life and the development of human civilizations. The regular rise and fall of ocean levels have affected coastal ecosystems and human activities for thousands of years. The Earth-Moon system is a fascinating subject of study, providing insights into the formation and evolution of planetary bodies. The differences in composition, the shared angular momentum, and the ongoing dance between Earth and its only natural satellite all tell a complex and intriguing story about our place in the cosmos. This photo was taken by a telescope in 1917. It shows a fuzzy blob with dark markings. Even respected astronomers back then thought these markings might be signs of vegetation. That idea was proven wrong when spacecraft started visiting Mars. The first was the Mariner 4 in 1965, which sent back grainy images of the surface. President Lyndon Johnson then reflected that life as we know it might be more unique than we thought. Today, many spacecraft have visited Mars. We now see a world with geological giants, like a canyon that spans half the planet called the Mariner Valley. the Grand Canyon on Earth would fit into one of its side channels. Mars also has huge volcanoes and evidence of lakes and possibly oceans. Currently, the Curiosity rover is exploring an old, dry lake bed and has found signs of organic molecules and minerals that form in standing water. We now know that Mars was Earth-like about 3 to 3.5 billion years ago, with rivers, oceans, and seas. It could have been a living world, but we don't know if life started there. This changes how we see Mars. A planet with water has everything needed to build a civilization and sustain life. Even if there weren't Martians billions of years ago, and even if there aren't Martian microbes today, there might be Martians in the future because the Martians will be us. Mars, often referred to as the Red Planet, has always captivated our imagination with its intriguing landscapes and the possibility of life beyond Earth. Among the many mysteries that Mars presents, one of the most compelling is the question of what happened to its water. Evidence suggests that billions of years ago, Mars had vast amounts of liquid water, flowing rivers, and possibly even large oceans. Today, however, Mars is a cold, dry desert with only trace amounts of water in its atmosphere and polar ice caps. So what caused this dramatic transformation? To understand the disappearance of water on Mars, we need to look back at the planet's early history. Geological features such as river valleys, lake beds, and mineral deposits indicate that Mars once had a much thicker atmosphere, which would have allowed liquid water to exist on its surface. This thicker atmosphere likely created a stable climate, maintaining the pressure and temperature needed for liquid water. However, over billions of years, Mars lost most of its atmosphere, leading to the arid conditions we observe today. One of the leading theories to explain the loss of Mars' atmosphere is the influence of the solar wind. The solar wind is a stream of charged particles emitted by the Sun. Unlike Earth, Mars does not have a global magnetic field to protect its atmosphere from these particles. Earth's magnetic field acts as a shield, deflecting the solar wind and preventing it from stripping away our atmosphere. Mars, however, lacks such a protective barrier. As a result, the solar wind directly interacts with the Martian atmosphere, gradually eroding it over time. This process, known as atmospheric sputtering, involves the solar wind particles colliding with atmospheric molecules, knocking them into space. As the Martian atmosphere thinned, the planet's ability to retain heat diminished. The drop in atmospheric pressure and temperature caused any remaining liquid water to either freeze or sublimate. Sublimation is the process where a solid turns directly into a gas, bypassing the liquid state. This process likely contributed to the loss of Mars's surface water, as the low pressure and temperature made it unsustainable for liquid water to remain. Mars's weak gravity also played a significant role in the loss of its atmosphere and water. Mars has only about 38% of Earth's gravity, which means it cannot hold onto its atmospheric gases as effectively as Earth can. Over time, lighter molecules like hydrogen and oxygen, which are essential components of water, escaped into space. This gradual escape of gases further depleted Mars' atmosphere, exacerbating the loss of water. Volcanic activity on Mars was once much more intense than it is today. Early in its history, Mars experienced significant volcanic eruptions, which released large amounts of gases into the atmosphere. These volcanic activities could have replenished the atmosphere and maintained a greenhouse effect, keeping the planet warm enough for liquid water. However, as volcanic activity decreased, so did the replenishment of the atmosphere. Without new gases being added, the atmosphere continued to thin, contributing to the planet's cooling and drying. Despite the loss of much of its atmosphere and surface water, Mars still holds significant amounts of water in the form of ice. Recent discoveries by rovers and orbiters have revealed vast deposits of water ice just beneath the surface, especially in the polar regions. Radar data from missions such as the Mars Reconnaissance Orbiter have detected large underground ice sheets, which could potentially hold more water than all of Earth's Great Lakes combined. Additionally, some scientists speculate that liquid water might exist in subsurface lakes, insulated by layers of ice and soil. These hidden reservoirs of water offer a glimpse into Mars' wetter past and provide hope for future exploration. The state of Mars' iron core plays a significant role in the planet's history and its current conditions. Unlike Earth, which has a molten iron core generating a strong magnetic field, Mars' iron core is largely solidified, resulting in a weak and patchy magnetic field. This lack of a protective magnetic field left Mars vulnerable to the solar wind, a stream of charged particles emitted by the Sun. Over billions of years, these particles stripped away much of Mars' atmosphere, leading to the loss of surface water. The weakened magnetic field not only influenced the atmospheric erosion, but also affected the planet's ability to sustain a climate capable of supporting liquid water. Understanding the fate of Mars' water is not only crucial for planetary science, but also for future human exploration. Water is essential for life and will be a vital resource for astronauts on Mars. It can be used for drinking, growing food, and producing oxygen and hydrogen for fuel. By unlocking the secrets of Mars' lost water, we can better prepare for human missions to the Red Planet. In situ resource utilization, the practice of using local materials for human needs, will be key to sustaining long-term missions on Mars. If we can locate and extract water from the Martian subsurface, it will greatly enhance the feasibility of establishing a permanent human presence on Mars. Mars serves as a natural laboratory for studying the evolution of planetary atmospheres and the factors that influence their stability. By comparing Mars with Earth and other planets, scientists can develop better models to predict the future of our own planet's climate and the potential for life on other worlds. In recent years, missions like NASA's Perseverance rover and the European Space Agency's ExoMars mission have focused on searching for signs of past life on Mars. These missions aim to study the planet's geology and search for biosignature, chemical or physical markers that indicate the presence of past or present life. The presence of water is a critical factor in these investigations, as it is a key ingredient for life as we know it. By understanding where water existed on Mars and how it interacted with the planet's geology, scientists can better assess the potential for ancient Martian life. The story of Mars' water is a complex tale of planetary change and the dynamic processes that shape our solar system. While many questions remain, each new discovery brings us closer to understanding this enigmatic planet. Mars's history of water, atmosphere, and climate evolution continues to captivate scientists and enthusiasts alike, driving the exploration and study of our neighboring world. This is a modern-day spacecraft picture of Mars. Everywhere we look, we see evidence of rivers, so Mars was a world that could have supported life about 3 billion years ago. Now we know there's water on Mars, minerals, and pretty much everything needed to support human life and a civilization. So Mars is not just a bringer of war or a scary red object in the sky, but a bringer of opportunity and hope. One of the most iconic and enduring features of our solar system is the Great Red Spot on Jupiter. This massive storm, larger than Earth itself, has been raging on Jupiter for at least 400 years, and possibly much longer. The Great Red Spot is a gigantic swirling storm that has fascinated astronomers and scientists since it was first observed. But what exactly is the Great Red Spot? And why has it lasted for so long? Let's dive into the details to uncover the secrets of this colossal storm. The Great Red Spot is essentially a high-pressure region in Jupiter's atmosphere, producing an anticyclonic storm, which means it rotates counterclockwise in the planet's southern hemisphere. This storm is so large that it can easily be seen through telescopes from Earth. In fact, it is about 1.3 times the diameter of our planet. The storm's edges spin faster than its center. The storm's distinct reddish color is one of its most intriguing features. Scientists are still not entirely sure what causes this striking hue. Some theories suggest that the red color comes from chemicals in Jupiter's atmosphere, such as phosphorus, sulfur, or organic compounds, which may be altered by the sun's ultraviolet light. Another theory is that the color could come from the depths of the storm itself, with different chemicals being churned up from below. Regardless of its origin, the red color makes the Great Red Spot stand out against the bands of white, brown, and yellow in Jupiter's turbulent atmosphere. One of the biggest mysteries about the Great Red Spot is its longevity. On Earth, storms usually last for a few days or weeks at most. However, the Great Red Spot has persisted for centuries. This incredible durability is partly due to Jupiter's unique atmospheric conditions. Jupiter is a gas giant, meaning it doesn't have a solid surface like Earth. Instead, it is composed mostly of hydrogen and helium, with traces of other gases. This allows storms to last much longer because there is no land to disrupt them. Additionally, Jupiter's immense size and rapid rotation contribute to the stability and longevity of the Great Red Spot. Jupiter's rapid rotation plays a crucial role in sustaining the Great Red Spot. The planet completes one rotation in just under 10 hours, which is much faster than Earth's 24-hour day. This rapid spinning creates strong jet streams that help to sustain and contain the Great Red Spot. These jet streams act like barriers, keeping the storm confined to its region and preventing it from dissipating. The interaction between these jet streams and the storm itself helps to maintain its structure and intensity over time. Despite its longevity, the Great Red Spot is not eternal. Observations over the past few decades show that the storm is gradually shrinking. When it was first measured in the late 1800s, the Great Red Spot was about 25,000 miles wide. Today, it is less than half that size. Scientists are closely monitoring this shrinkage to understand why it is happening and what it could mean for the future of the storm. The reasons for this gradual contraction are not fully understood, but it could be due to changes in the dynamics of Jupiter's atmosphere or interactions with other storms and atmospheric features. The dynamics within the Great Red Spot are complex and not yet fully understood. Inside the storm, winds can reach speeds of up to 400 miles per hour. These powerful winds create towering clouds that can rise high above the surrounding atmosphere. The storm also has a layered structure, with different temperatures and wind speeds at various altitudes. Studying these layers helps scientists learn more about the storm's behavior and its impact on Jupiter's atmosphere. The top of the Great Red Spot is much cooler than the clouds around it, indicating that the storm extends deep into Jupiter's atmosphere. In recent years, NASA's Juno spacecraft has provided unprecedented insights into the Great Red Spot. Juno, which has been orbiting Jupiter since 2016, carries a suite of instruments designed to study the planet's atmosphere, magnetic field, and internal structure. Juno's close flybys of the Great Red Spot have revealed new details about the storm's depth and composition. For example, Juno has shown that the storm extends much deeper into Jupiter's atmosphere than previously thought, possibly hundreds of miles. This depth suggests that the Great Red Spot is a towering structure with deep roots in the planet's gaseous envelope. The Great Red Spot also offers a window into understanding other planetary atmospheres, including those of exoplanets, planets outside our solar system. By studying this giant storm, scientists can develop models to predict weather patterns on other gas giants and potentially habitable worlds. This knowledge expands our understanding of how atmospheres work across the universe. The insights gained from the Great Red Spot help scientists to identify similar features on exoplanets and understand the atmospheric dynamics of distant worlds. The mystery of the Great Red Spot continues to capture our imagination. It serves as a reminder of the immense and powerful forces at play in our solar system. Each new discovery about the Great Red Spot brings us closer to unraveling its secrets, but also highlights how much we still have to learn about Jupiter and other giant planets. The storm's persistence and changing nature make it a dynamic laboratory for studying the behavior of atmospheres under extreme conditions. In addition to its scientific significance, the Great Red Spot has also become a cultural icon. It has been featured in countless works of science fiction, art, and literature, symbolizing the mysteries and wonders of our solar system. The storm's vivid appearance and enduring presence make it a favorite subject for both professional astronomers and amateur stargazers alike. Observing the Great Red Spot through a telescope is a thrilling experience that connects us to the vast and dynamic universe beyond our planet. Understanding the Great Red Spot also helps us appreciate the delicate balance of Earth's own atmosphere. While our planet's storms are much smaller and shorter-lived, the underlying principles of atmospheric dynamics are similar. The future of the Great Red Spot remains uncertain. Will it continue to shrink and eventually disappear, or could it stabilize and persist for many more centuries? Scientists are eager to find out, and ongoing observations from missions like Juno will be crucial in answering these questions. The data collected by Juno and future missions will help scientists to build more accurate models of Jupiter's atmosphere and understand the long-term behavior of its most famous storm. Jupiter, the largest planet in our solar system, is known for its many fascinating features, from its iconic Great Red Spot to its vibrant bands of clouds. But one of its most dramatic features is the series of scars on its face, caused by impacts from comets and asteroids. These impact scars offer a unique window into the violent history of our solar system and the powerful forces at play on Jupiter. One of the most famous events that left scars on Jupiter occurred in July 1994, when the comet Shoemaker-Levy 9 collided with the planet. This was the first time humans had the opportunity to witness such a cosmic event in real time. Shoemaker-Levy 9 was discovered by astronomers Carolyn and Eugene Shoemaker and David Levy in March 1993. The comet had broken apart into several fragments, likely due to a previous close encounter with Jupiter's strong gravitational field. As the fragments of Shoemaker-Levy 9 approached Jupiter, astronomers around the world prepared to observe the collisions. When the impacts began on July 16, 1994, they produced spectacular results. Each fragment crashed into Jupiter's atmosphere at a speed of about 60 kilometers per second, releasing immense amounts of energy. The impacts created enormous fireballs, some rising as high as 3,000 kilometers above the cloud tops. These collisions left dark, bruise-like scars on Jupiter's surface, which were visible even through small telescopes on Earth. The largest impact, caused by fragment G, left a scar over 12,000 kilometers wide, larger than the diameter of Earth. The scars, composed of dark debris, gradually faded over the following months, but their initial visibility highlighted the massive scale of these impacts. The event provided invaluable data to scientists, offering insights into the behavior of comets and the dynamics of planetary atmospheres. The scars from Shoemaker-Levy 9 were not permanent, but they underscored the vulnerability of even the largest planets to cosmic collisions. Jupiter's immense gravity makes it a prime target for comets and asteroids, acting as a sort of vacuum cleaner for the solar system. By capturing or redirecting these objects, Jupiter helps protect the inner planets, including Earth, from potential impacts. However, this protective role also means that Jupiter's atmosphere frequently bears the brunt of these collisions. In more recent years, amateur astronomers have continued to spot new impact events on Jupiter. On July 19, 2009, another significant impact was observed by Australian amateur astronomer Anthony Wesley. He noticed a new dark spot near Jupiter's south pole, similar in appearance to the scars left by Shoemaker-Levy 9. Follow-up observations confirmed that this spot was caused by the impact of a comet or asteroid. This event once again demonstrated Jupiter's role as a guardian of the inner solar system, taking the hit from a potentially dangerous object. The scars on Jupiter's face are not only a testament to its turbulent environment, but also a reminder of the dynamic nature of our solar system. These impact events help scientists understand the frequency and scale of collisions in space, shedding light on the processes that have shaped the planets over billions of years. Studying these impacts on Jupiter can also provide clues about the early history of the solar system, a time when such collisions were much more common. Jupiter's ability to capture and absorb impacts also has implications for the study of exoplanets, or planets outside our solar system. By understanding how Jupiter interacts with comets and asteroids, scientists can develop models to predict the behavior of gas giants in other planetary systems. This knowledge is crucial for assessing the potential habitability of exoplanets, as gas giants like Jupiter may play a similar protective role in those systems. In addition to its role as a cosmic shield, Jupiter's scars offer insights into the composition and structure of its atmosphere. When an impact occurs, it releases a burst of energy that can penetrate deep into the planet's atmosphere. By observing the aftermath of these impacts, scientists can study the resulting disturbances and gather information about the atmospheric layers. This helps them understand the complex weather patterns and chemical processes occurring on Jupiter. The scars left by impacts also reveal the sheer power of these collisions. The energy released by the Shoemaker-Levy 9 impacts, for example, was equivalent to millions of nuclear bombs exploding simultaneously. Such events underscore the importance of monitoring near-Earth objects and developing strategies to mitigate potential threats from space. Jupiter's scars are a stark reminder of the forces that shape our solar system. They highlight the ongoing dance of celestial bodies and the constant change that characterizes the cosmos. While the scars may eventually fade, the knowledge gained from studying them endures, contributing to our understanding of planetary science and the dynamics of our solar system. Mars continues to surprise scientists with its mysterious phenomena, and one of the most intriguing discoveries is the presence of strange dark streaks on its surface that appear to ooze and flow. These streaks, known as recurring slope lineae, are found on steep slopes like crater walls and canyon sides. They seem to darken and lengthen during the warm seasons and fade away when it gets colder. Scientists believe these streaks might be caused by salty water that temporarily flows down the slopes when temperatures rise, although the exact source and nature of the water remain unknown. The idea of water on Mars is not new. Mars shows many signs that it once had a lot of liquid water. Long ago, Mars had rivers, lakes, and maybe even oceans. We can see old riverbeds and lake basins on its surface, However, today Mars is mostly dry, with only a little ice at its poles and some water vapor in its thin atmosphere. These dark streaks were first noticed by the Mars Reconnaissance Orbiter, a spacecraft that has been studying Mars from orbit since 2006. The MRO has a special camera called the High-Resolution Imaging Science Experiment that can take very detailed pictures of the Martian surface. This pattern suggested that the streaks might be linked to liquid water, which could flow when it's warmer and freeze or dry up when it's colder. To better understand the RSL, scientists looked at the conditions on Mars where these streaks appear. They found that these streaks usually form on slopes facing the Sun, where it gets warm enough for ice to melt. However, Mars is still very cold compared to Earth, and pure water would freeze quickly. This led scientists to think that the water in the RSL must be mixed with salts. Salty water can stay liquid at lower temperatures because the salts lower the freezing point of water, similar to how salt is used to melt ice on roads during winter. The exact source of the water in these streaks is still a mystery. Some scientists think the water might come from underground ice that melts and seeps out. Others believe the water could come from the atmosphere, with water vapor being absorbed by salts in the soil and then turning into liquid when it gets warm. Both ideas are possible, but more research is needed to find the true source. Understanding the RSL is important for several reasons. First, if there is liquid water on Mars today, it increases the chances that life could exist there, even if only in tiny microbial forms. Water is essential for life as we know it, so finding liquid water on Mars is a big step in the search for Martian life. Second, the presence of water is important for future human missions to Mars. Astronauts could use this water for drinking, growing food, and making fuel. However, there are also challenges and risks. The salty water might be very different from the water we are used to on Earth, and it could be harmful to both humans and any Earth microbes we bring with us. It's important to study these streaks carefully to understand what kind of water they contain and how it might affect future missions. In conclusion, the discovery of these dark, oozing streaks on Mars is a fascinating development in our understanding of the Red Planet. They suggest that liquid water might still exist on Mars today, at least during the warm seasons. This opens up new possibilities for finding life and supports the idea that Mars was once a much wetter planet. As we continue to explore Mars, each new discovery brings us closer to understanding its mysteries and prepares us for the day when humans might set foot on its surface. The oozing streaks of Mars are just one of many clues that will help us unlock the secrets of our neighboring planet. In March 2004, NASA's Mars Exploration Rover Opportunity had just finished its 283 million-mile journey from Earth to Mars. In the following days, Opportunity took many photos of Mars' surface, but one picture surprised and confused the mission team. It showed what looked like a fuzzy white bunny. This object quickly became known as the Martian Bunny. The Martian Bunny caused a lot of excitement and confusion among scientists. They wondered what it could be. Was it a piece of the rover, a strange rock, or something else entirely? The object appeared in several images taken by the rover, showing it from different angles. It had a fluffy, bunny-like appearance, which made it even more mysterious and intriguing. As scientists examined the images, they started to develop theories about what the Martian Bunny could be. One idea was that it might be a piece of the rover itself, possibly a piece of insulation material, or a piece of debris that had fallen off during landing. This theory made sense because the object did not look like a natural rock or any other known Martian feature. It seemed to be something out of place. However, before scientists could study it further, the Martian Bunny did something unexpected and it disappeared. In later images taken by the rover, the mysterious object was no longer visible. This sudden disappearance added another layer to the mystery. How could an object just vanish from the Martian surface? There are a few possible explanations for the disappearance of the Martian Bunny. One idea is that it was a light piece of material, like plastic or fabric, that got blown away by the wind. Mars has strong winds that can move dust and small objects across the surface. If the Martian Bunny was a piece of lightweight debris, it could have been lifted and carried away by the wind, disappearing from the rover's camera view. Another possibility is that the object was buried by Martian dust. Mars is a dusty planet, and dust storms can cover objects very quickly. If a dust storm passed over the area where the Martian Bunny was located, it might have buried the object under a layer of dust, making it invisible to the rover's cameras. While the true identity of the Martian Bunny may never be known, the mystery highlights the challenges and surprises of exploring another planet. Mars is a complex and dynamic world, and even small, unexplained events, like the appearance and disappearance of the Martian Bunny, can teach us a lot about the planet. Each discovery, no matter how small, adds to our understanding of Mars and prepares us for future missions. When Johnson, a scientist with the US Geological Survey, was intrigued by the mysterious object, he was assigned to find out more about it. He soon found the bunny in other images taken by the rover's navigation camera and used special software from NASA's Jet Propulsion Laboratory to measure its size, which was about the same as a tennis ball. Then, there it was again. In a photo of the rover's lander, Johnson saw a small white object that looked similar to the bunny seen in earlier pictures. The team thought a light wind had blown the object to a new spot, under one of the ramps meant to help the rover roll onto the Mars surface. Scientists never confirmed exactly what it was, but they believed it was probably just a piece of soft material from the landing vehicle. The landing vehicles were made of many different materials, but the most likely candidate was the white felt that surrounded each of the 3 airbag gas generators. In conclusion, the Martian Bunny is one of the many fascinating puzzles that Mars presents. It appeared suddenly in the images taken by the Opportunity rover, causing excitement and curiosity, and then vanished just as mysteriously. Whether it was a piece of the rover, a lightweight object blown away by the wind, or something buried by dust, the Martian Bunny reminds us of the unpredictable and surprising nature of space exploration. As we continue to study Mars, we can expect many more mysteries and discoveries that will deepen our understanding of this intriguing planet. Saturn, the 6th planet from the Sun, is a world of wonders and mysteries. Among its most fascinating features is the bizarre hexagonal storm that swirls around its north pole. This geometric storm has captured the curiosity of scientists and space enthusiasts alike, as it presents a phenomenon unlike anything seen on Earth or any other planet in our solar system. Let's delve into the details of this remarkable and puzzling storm. Discovered by NASA's Voyager spacecraft during its flybys in the early 1980s, the hexagonal storm on Saturn is a massive and persistent weather pattern. Unlike the circular storms we are familiar with on Earth, this storm has a distinct 6-sided shape, resembling a hexagon. Each side of the hexagon is roughly 14,500 kilometers long, making it more than twice the diameter of Earth. The storm also contains a powerful jet stream, with wind speeds reaching up to 320 kilometers per hour. What makes this hexagonal storm so intriguing is not just its size and shape, but also its stability. The storm has persisted for decades, showing little change in its structure or position. While storms on Earth can last for days or weeks, this hexagon has remained in place for at least 40 years, and possibly much longer. Scientists have proposed several theories to explain the formation and persistence of Saturn's hexagonal storm. One leading theory suggests that the hexagon is formed by a standing wave pattern in Saturn's atmosphere. On Earth, standing waves can occur in oceans and the atmosphere, creating stable patterns that do not move with the flow of air or water. Similarly, the hexagon on Saturn might be a standing wave created by the interaction of Saturn's atmosphere with its rapid rotation and internal heat. Saturn's atmosphere is composed mainly of hydrogen and helium, with trace amounts of other gases like methane, ammonia, and water vapor. The planet's rapid rotation, completing one spin in just over 10 hours, creates strong jet streams and turbulent weather patterns. These jet streams can interact in complex ways, leading to the formation of stable structures like the hexagon. The standing wave theory suggests that the hexagon is a result of these interactions, with the wave pattern locking the storm into its distinctive shape. Another theory proposes that the hexagon is related to the unique properties of Saturn's atmosphere and its layered structure. Saturn's atmosphere has different layers, each with its own temperature, pressure, and composition. These layers can interact in ways that create stable, geometric patterns. Laboratory experiments have shown that similar hexagonal patterns can form in rotating fluids, supporting the idea that the hexagon is a natural outcome of Saturn's atmospheric dynamics. One of the most intriguing aspects of the hexagonal storm is its color. In images taken by NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, the hexagon appears in shades of blue and gold. The color variations are likely due to seasonal changes in Saturn's atmosphere. During the northern winter, the hexagon appears blue, possibly due to the absence of sunlight and the resulting condensation of certain gases. As spring and summer approach, the hexagon changes to a more golden hue, likely due to increased sunlight and the production of photochemistry hazes. For the first 5 years of Cassini's mission at Saturn, it was impossible to see the hexagon at the planet's north pole in visible light, because it was winter there. Winter on Saturn lasts about 7 years and keeps the North Pole in darkness. But in December 2009, spring arrived, and the sun began to shine on the North Pole again. This allowed Cassini to capture the first detailed images of Saturn's hexagon, showing features never seen before. Physicists at the University of Oxford helped explain the hexagon by simulating the interaction between Saturn's atmosphere and a spinning jet stream. They discovered that by changing the speed of the jet stream and atmosphere, they could create different shapes, including a hexagon. It turns out that Saturn's hexagon is formed by an intense jet stream, mixing with the surrounding atmosphere, and at its center is a massive rotating storm that has been there for decades. In 2013 and 2017, Cassini took more close-up images of the hexagon. These images were combined to create 2 videos from 2013 and 2017. However, a new mystery emerged. What caused the hexagon's color to change over those 4 years? The Cassini mission provided a set of data about Saturn's hexagon, revealing details that were previously unknown. For example, Cassini observed a massive hurricane-like storm at the center of the hexagon, with a clearly defined eye and high-speed winds. This central storm is surrounded by towering clouds that reach heights of up to 100 kilometers above the surrounding cloud tops. The data from Cassini also showed that the hexagon extends deep into Saturn's atmosphere, indicating that it is not just a surface feature, but a complex, multi-layered structure. Understanding Saturn's hexagonal storm is not just about solving a planetary puzzle, it also has broader implications for our understanding of atmospheric dynamics. The study of this storm can provide insights into the behavior of fluids and gases under extreme conditions, helping scientists to develop better models of weather patterns on Earth and other planets. The hexagon also serves as a natural laboratory for studying the effects of rotation, convection, and wave interactions in planetary atmospheres. The persistence and stability of Saturn's hexagonal storm also raise questions about the long-term evolution of planetary weather systems. How do such patterns form, and what factors determine their longevity? By studying the hexagon, scientists can gain a better understanding of the processes that drive weather patterns on gas giants and other planets, both in our solar system and beyond. In recent years, scientists have used computer simulations to model the hexagon and test different hypotheses about its formation. These simulations have shown that rotating fluids can indeed produce stable, hexagonal patterns under certain conditions. By adjusting the parameters of these models, researchers can explore how different factors such as Saturn's rotation rate, atmospheric composition, and internal heat contribute to the formation and maintenance of the hexagon. The hexagonal storm on Saturn continues to be a subject of active research and fascination. Each new discovery adds to our understanding of this extraordinary feature and the dynamic processes that shape planetary atmospheres. As future missions to Saturn and other gas giants are planned, scientists hope to gather even more data to unlock the secrets of the hexagon and other mysterious phenomena. In conclusion, the hexagonal storm on Saturn is a striking and enigmatic feature that challenges our understanding of planetary weather. Its geometric shape, immense size, and long-lasting stability make it a unique phenomenon in our solar system. By studying the hexagon, scientists can gain valuable insights into the dynamics of Saturn's atmosphere and the broader principles that govern fluid behavior and atmospheric patterns. As we continue to explore the wonders of our solar system, the hexagonal storm on Saturn remains a compelling reminder of the complexity and beauty of the universe. Perhaps the biggest space mystery ever is whether we are alone in the universe or even in our solar system. Recently, we've found hints that the answer might be out there, maybe even on one of the moons of Jupiter and Saturn. Water is essential for life as we know it. Astrobiologists, who study the possibility of life beyond Earth, say other necessary ingredients include certain chemicals and a constant source of energy. Until recently, Earth was the only known world with liquid water. Now we know that at least two other places, Jupiter's moon Europa and Saturn's moon Enceladus, have global oceans. There are also hints that water exists in other places. But what about the other ingredients for life? The icy moons Europa and Enceladus might have those too. When the Cassini spacecraft discovered a plume of water vapor and icy particles shooting from Saturn's moon Enceladus, scientists wanted to know more. Cassini was originally supposed to fly by Enceladus 3 times, but it ended up making 23 passes, learning more about the moon's chemistry and the plume each time. They found a salty ocean beneath Enceladus's icy surface and strong evidence of hydrothermal vents. These vents, similar to those at the bottom of Earth's oceans, release chemicals that support tiny shrimp and other creatures. If Enceladus has similar vents, it could have the necessary chemistry and energy for life. Alien shrimp, anyone? Meanwhile, on Jupiter's moon Europa, clues from the Galileo mission suggest it also has a global ocean. Later, NASA's Hubble Space Telescope detected possible plumes there too. To find out more, NASA is developing a new spacecraft called Europa Clipper, designed to study Europa and investigate this mystery further. These moons have conditions that could be similar to those in Earth's deep oceans, where life thrives around hydrothermal vents. On Earth, these vents support ecosystems teeming with life, including shrimp, crabs, and various microorganisms. These creatures do not rely on sunlight for energy. Instead, they depend on the chemical energy released by the vents, showing that life can exist in extreme environments. Europa and Enceladus both have thick ice crusts covering their oceans. Scientists believe that beneath these icy shells there could be warm, salty oceans that may be hospitable to life. The ice acts as a protective layer, shielding the oceans from the harsh radiation of space. This makes these moons some of the most promising places to search for life beyond Earth. The discovery of plumes on Enceladus was a major breakthrough. These plumes shoot out from cracks in the moon's ice shell, known as tiger stripes, and extend hundreds of kilometers into space. Cassini flew through these plumes, analyzing their composition and discovering water vapor, ice particles, and organic molecules. The presence of these organic molecules suggests that Enceladus has the building blocks of life. Cassini's findings also indicated that the plumes contain salts and other minerals, hinting at the presence of hydrothermal activity on the ocean floor. On Earth, hydrothermal vents are home to diverse ecosystems, fueled by the chemicals released from the vents. If similar conditions exist on Enceladus, it raises the possibility that life could be thriving in its hidden ocean. NASA's planned Europa Clipper mission aims to explore Europa in more detail. Scheduled to launch in October 2024, the Europa Clipper will conduct detailed study of Europa's ice shell and subsurface ocean. The spacecraft will carry instruments to analyze the ice and detect signs of water vapor plumes. By flying close to Europa, the Europa Clipper will gather data to help scientists understand the moon's habitability and potential for life. Europa's surface is covered with a network of cracks and ridges, indicating that its ice shell is active and possibly influenced by the ocean below. The Galileo mission found evidence of a magnetic field around Europa, which is thought to be generated by a salty, conductive ocean beneath the ice. This magnetic field is another piece of evidence supporting the existence of a subsurface ocean. The potential for life on Europa and Enceladus extends beyond just having liquid water and organic molecules. These moons also have sources of energy that could sustain life. On Earth, life thrives in extreme environments where energy comes from chemical reactions rather than sunlight. The hydrothermal vents on the ocean floors of Europa and Enceladus could provide the necessary energy for life to exist. In addition to the Europa Clipper, other future missions are being planned to explore these icy moons further. One such mission is the Enceladus Life Finder, which aims to sample and analyze the plumes of Enceladus in even greater detail. By studying the composition of the plumes, scientists hope to detect signs of life, or at least the conditions that could support life. The search for life on Europa and Enceladus is part of a broader effort to understand the potential for life elsewhere in the solar system and beyond. These moons offer unique environments that could help us answer one of the most profound questions in science. Are we alone in the universe? If life is found on Europa or Enceladus, it would have profound implications for our understanding of biology and the potential for life beyond Earth. It would suggest that life can arise in a variety of environments and that the universe may be teeming with life in places we have yet to discover. Uranus, the seventh planet from the Sun, is a fascinating world in our solar system. One of its most unusual features is its extreme axial tilt. Unlike other planets that rotate with their axes more or less perpendicular to their orbital planes, Uranus is tilted at an angle of about 98 degrees. This means that Uranus essentially rolls around the Sun on its side, with its poles taking turns facing the Sun directly. Let's dive into the details of this strange axial tilt and explore the mysteries surrounding it. The odd axial tilt of Uranus is believed to be the result of a colossal impact that occurred billions of years ago, soon after the planet formed. According to this theory, a massive object, possibly the size of Earth or even larger, collided with Uranus, causing it to tip over onto its side. This cataclysmic event would have had a profound impact on Uranus's rotation and orbit, resulting in the extreme tilt we observe today. While this theory is widely accepted, the exact details of the impact and the object involved remain unknown. Some scientists propose that it wasn't just one impact, but a series of collisions with smaller objects that gradually shifted Uranus's tilt to its current extreme angle. These smaller impacts could cumulatively alter the planet's rotational axis without necessarily destroying it or significantly changing its overall structure. The extreme tilt of Uranus has significant effects on the planet's seasons and climate. On Earth, we experience relatively mild seasonal changes because our planet's axial tilt is only about 23.5 degrees. However, the 98-degree tilt of Uranus means that each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness, as the planet takes 84 Earth years to complete one orbit around the Sun. This creates some of the most extreme seasonal variations in the solar system. During the long summer, one pole of Uranus stays in continuous sunlight, while the other side remains in darkness. As Uranus continues its orbit, the situation gradually reverses, with the opposite pole experiencing summer. This unique axial tilt leads to extreme temperature fluctuations and unusual weather patterns. The planet's atmosphere, composed mainly of hydrogen, helium, and methane, exhibits dynamic and complex behavior as a result of these extreme seasonal changes. The atmosphere of Uranus is another point of interest. The planet's blue-green color comes from the methane in its atmosphere, which absorbs red light and reflects blue and green light. This gives Uranus its distinctive hue. The atmosphere is also marked by high-speed winds that can reach speeds of up to 560 miles per hour. These winds, combined with the planet's axial tilt, create turbulent weather systems and dramatic cloud formations. One of the most intriguing aspects of Uranus's atmosphere is the presence of dark spots, similar to the Great Red Spot on Jupiter. These dark spots are thought to be storms or vortices, and their appearance can change over time. Observations by the Hubble Space Telescope and other instruments have revealed these features, providing valuable insights into the atmospheric dynamics of Uranus. The peculiar tilt of Uranus also affects its magnetic field. Unlike Earth, whose magnetic field is roughly aligned with its rotational axis, Uranus's magnetic field is tilted at an angle of about 59 degrees relative to its rotational axis. This misalignment means that the magnetic field is off-center and more complex than Earth's. The magnetic field of Uranus is believed to be generated by a layer of ionic slush in the planet's interior, composed of water, ammonia, and methane. This layer, combined with the planet's rotation, creates the unusual magnetic field. The study of Uranus's magnetic field provides important clues about the planet's interior structure. Scientists believe that the core of Uranus is made up of rock and metal, surrounded by a thick layer of icy materials. The outermost layer consists of hydrogen and helium gas, similar to the composition of Jupiter and Saturn. Understanding the magnetic field helps researchers develop models of Uranus's interior and its formation history. In addition to its axial tilt and magnetic field, Uranus has a system of rings and moons that add to its unique character. The rings of Uranus were discovered in 1977 and are much darker and narrower than the rings of Saturn. These rings are composed mainly of large particles and are believed to be relatively young, possibly formed from the debris of shattered moons or captured objects. Uranus has 27 known moons, with the largest being Titania, Oberon, Umbriel, Ariel, and Miranda. These moons are named after characters from the works of William Shakespeare and Alexander Pope. Each moon has its own unique features and geology. For example, Miranda, the innermost of the large moons, has a highly varied surface with deep canyons, ridges, and regions that appear to have been heavily reshaped by geological processes. This diversity suggests a complex history of internal activity and resurfacing. The peculiar characteristics of Uranus have made it a subject of great interest for planetary scientists. However, despite its fascinating features, Uranus has been relatively underexplored. The only spacecraft to visit Uranus was Voyager 2, which flew by the planet in 1986. Voyager 2 provided valuable data and images, but much remains to be learned about this distant world. Future missions to Uranus could reveal more about its atmosphere, magnetic field, rings, and moons, shedding light on the mysteries of this tilted giant. There is also a hypothesis that suggests the influence of a large moon or multiple moons that exerted gravitational forces strong enough to tilt Uranus over time. However, the current moons of Uranus are relatively small compared to the planet, making this less likely compared to the giant impact hypothesis. The study of Uranus also has broader implications for our understanding of the solar system. By learning more about Uranus, scientists can gain insights into the processes that shape planetary formation and evolution. Uranus is considered an ice giant because it has a higher proportion of icy materials compared to the gas giants, Jupiter and Saturn. Studying ice giants like Uranus and Neptune can help researchers understand the diversity of planetary types and the conditions that lead to their formation. In recent years, there has been growing interest in sending a dedicated mission to Uranus. Such a mission could involve an orbiter and possibly a probe to study the planet's atmosphere in detail. By conducting long-term observations, scientists could monitor seasonal changes, atmospheric dynamics, and magnetic field variations. Additionally, close-up studies of Uranus's rings and moons could provide new insights into their composition and history. In 1972, a remarkable spacecraft named Pioneer 10 set off on an exciting mission to explore the asteroid belt and the giant gas planets in the outer part of our solar system. Traveling at 32,000 miles per hour, Pioneer 10 left Earth and paved the way for future missions, like the Voyager probes. Pioneer 10's mission was very successful, but it had its challenges. The probe carried a hidden problem that puzzled scientists for decades. Known as the luckiest spacecraft ever launched, Pioneer 10 faced many malfunctions. In the early 1980s, while it was still communicating with Earth, scientists noticed something strange. Pioneer 10 was slowing down and veering off course, as if an unknown force was pulling it back towards the Sun. For about 15 years, researchers studied and analyzed the data but couldn't solve the mystery. The unexplained slowdown eventually stopped, leaving behind one of the greatest enigmas in spaceflight history. This phenomenon, called the Pioneer Anomaly, remains unsolved. Even today, the flyby anomaly continues to puzzle scientists. This glitch challenges our understanding of spaceflight and keeps us searching for answers. The Pioneer Anomaly is a reminder that, despite our advances in space exploration, there are still mysteries in the universe that test our knowledge and spark our curiosity. Pioneer 10 was NASA's groundbreaking mission to explore the outer planets. Named after the brave pioneers who settled the western United States, the probe aimed to boldly go where no spacecraft had gone before. Pioneer 10 achieved remarkable milestones, including several firsts in space exploration. It was the first spacecraft to travel beyond Mars, cross the asteroid belt, and reach the gas giant Jupiter. Pioneer 10 made history as the first spacecraft to use an all-nuclear power supply and take a path beyond our solar system. Although it was meant for a 21-month mission, Pioneer 10 exceeded expectations and operated for over 30 years. In January 2003, after a long journey, it sent its final signal back to Earth. Today, Pioneer 10 continues to drift through space, more than 11 billion miles away, moving in the opposite direction of the Sun's motion through the galaxy. Pioneer 11, the twin to Pioneer 10, launched in 1973 and embarked on its own journey. Like Pioneer 10, it passed Mars, navigated the asteroid belt, and reached Jupiter. Pioneer 11 then made history as the first spacecraft to fly by Saturn. Unlike its twin, Pioneer 11 left Saturn on a different path, heading out of the solar system at a 90-degree angle to Pioneer 10, towards the center of the galaxy in the direction of the constellation Sagittarius. In 1995, NASA received the last signal from Pioneer 11, marking the end of its communication. It silently vanished into space, leaving behind a legacy of exploration. Both Pioneer 10 and 11 also left behind a puzzle that has baffled scientists for decades. Shortly after Pioneer 10 and 11 ventured beyond Jupiter and Saturn, their navigators noticed something strange. Both spacecraft were slowing down more than expected, as if an unknown force was gently pulling them back towards the Sun. While some deceleration due to the Sun's gravity was expected, the data showed an excessive slowdown that couldn't be easily explained. The deceleration was very small, just 1/10-billionth of Earth's gravitational acceleration. In 1998, John Anderson of JPL and his colleagues calculated that the spacecraft were slowing down at a rate of about 300 inches per day. This tiny difference had significant implications. The Pioneers ended up thousands of kilometers closer to Earth each year than expected, eventually falling short of their predicted locations by distances similar to the gap between Earth and the Moon. Year after year, the spacecraft deviated by a few thousand kilometers from their expected positions. At first, this didn't raise many concerns, but as time passed, it became clear that this small deceleration persisted as the spacecraft traveled deeper into space. The Pioneer Anomaly remains one of the greatest mysteries in space exploration, challenging our understanding and sparking curiosity about the forces at play in the cosmos. This mystery adds to the many questions we have about the universe, pushing us to seek answers and explore further. The question of how the universe began from nothing is one of the most interesting questions in cosmology. One of the primary theories in modern cosmology is the Big Bang theory, which explains how our universe began and evolved. Imagine every star, planet, and galaxy packed into an incredibly hot and dense point. Scientists believe this is how everything started about 13.8 billion years ago. Since then, the universe has been expanding and cooling down. This tiny point exploded in an event called the Big Bang, and from that moment, the universe started growing and cooling. The term Big Bang can be somewhat misleading, as it suggests an explosion occurring in space. However, the Big Bang was not an explosion in space. It was an expansion of space itself. In the first fractions of a second after the Big Bang, the universe expanded exponentially in a period known as cosmic inflation. During this time, the universe grew from an almost infinitesimally small point to a macroscopic scale. As the universe expanded, it cooled down, allowing energy to transform into particles of matter. These particles combined to form simple elements like hydrogen and helium. Over billions of years, these elements would merge under the force of gravity to form stars, galaxies, and planets. These elements were formed in the first few minutes after the Big Bang when the universe cooled enough for protons and neutrons to make nuclei. But how do we know the Big Bang happened? The Big Bang theory is supported by a lot of evidence. One key piece is the cosmic microwave background radiation, which is an afterglow from the early universe. This radiation gives us a picture of the universe just 380,000 years after the Big Bang. Before that, the universe was so hot and dense that we couldn't take pictures of it. This radiation was discovered by accident in 1965 by Arno Penzias and Robert Wilson. The CMB's uniformity and slight fluctuations support the idea of cosmic inflation and the rapid expansion of the universe. Another piece of evidence is the redshift of galaxies. This means that galaxies are moving away from us, showing that the universe is expanding and growing. This was first observed by Edwin Hubble in the 1920s. The farther away a galaxy is, the faster it seems to be moving away from us. This supports the idea that the universe was once much smaller, hotter, and denser. But the Big Bang theory also raises some big questions. For example, it doesn't explain what happened before the Big Bang or what lies beyond the part of the universe we can see. It also introduces the idea of cosmic inflation, which is a rapid expansion that happened right after the Big Bang. Before the discovery of cosmic microwave background radiation, there was a popular idea known as the steady-state theory. This theory suggested that the universe has no beginning or end. Instead, it stays the same overall, even though it's expanding by constantly creating new matter. This theory was popular in the 1940s, but lost support when scientists discovered the cosmic microwave background radiation in 1965, which strongly supports the Big Bang theory. Additionally, theories such as the cyclic model, which suggests the universe undergoes endless cycles of expansion and shrinking. After the Big Bang, the universe expanded and cooled. In the beginning, it was a hot, dense soup of particles. As it expanded, it cooled down, allowing particles to come together and form the first atoms. These atoms then formed the first stars and galaxies. The universe's expansion continues today, with galaxies moving away from us in all directions. Let's think even further back. The first long-lived particles of any kind were protons and neutrons, which together make up the atomic nucleus. These appeared around 1/10,000th of a second after the Big Bang. Before that, there was really no material as we know it. But physics allows us to trace the timeline even further back to processes that happened before any stable matter existed. To understand how the universe could begin from nothing, we need to explore the strange world of quantum mechanics. In the realm of quantum physics, nothing is not the absence of anything, but rather a state of vacuum energy, where particles constantly pop in and out of existence. This phenomenon is known as quantum fluctuations. Quantum fluctuations occur in what is known as the quantum vacuum, a state with the lowest possible energy where particles can momentarily appear and then vanish. According to the laws of quantum mechanics, it is possible for these fluctuations to lead to the creation of a universe. In this context, nothing is an energetic state that can give rise to matter and energy. One of the key concepts in understanding this process is Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be known to arbitrary precision. This principle allows for the temporary creation of particles from the vacuum, as long as they disappear quickly enough to comply with the law of conservation of energy. Quantum fluctuations can cause particles to appear and then disappear shortly after. This might sound strange, but such particles have been observed in many experiments. The vacuum of space is filled with particles constantly being created and destroyed, seemingly out of nothing. This suggests that the quantum vacuum is actually something rather than nothing. Where did space-time itself come from? To answer this, we need to go back to the very beginning, into the Planck epoch. This period was so early in the universe's history that our best theories of physics no longer work. It happened only a tiny fraction of a second after the Big Bang. During this time, space and time themselves were affected by quantum fluctuations. Usually, physicists use quantum mechanics for tiny particles and general relativity for large cosmic scales. But to understand the Planck epoch, we need a complete theory of quantum gravity that combines the two. We don't have a perfect theory of quantum gravity yet, but there are ideas like string theory and loop quantum gravity. These theories suggest that ordinary space and time come from deeper, microscopic processes. What we experience as space and time is the result of quantum processes, which are hard for us to understand because we are used to the large-scale world. Quantum fluctuations happen constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a short moment, and then destroy each other. This phenomenon is known as quantum foam, but quantum fluctuations alone don't explain the universe's vast scale and complexity. There is dark energy, a mysterious force that fills all of space and accelerates the expansion of the universe. While we don't fully understand dark energy, it's believed to play a crucial role in the creation and evolution of the cosmos. So how did we get from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded exponentially, setting the stage for the formation of galaxies, stars, and planets. In the Planck epoch, our usual understanding of space, time, and cause and effect breaks down. Despite this, all candidate theories of quantum gravity describe something physical happening in the Planck epoch, some quantum precursor to ordinary space and time. But where did that come from? Even if causality doesn't work in the usual way, it might still be possible to explain parts of the Planck epoch universe in terms of other parts. Unfortunately, our best physics can't provide clear answers yet. Until we develop a theory of everything, we won't be able to give a definitive answer. The most we can say with confidence is that physics has not found any confirmed instances of something arising from nothing. When we look around, everything we see is made of matter. Everything we touch, see, and interact with is made up of tiny particles. Over billions of years, these particles have come together to form galaxies and stars. They all follow the same physical laws and exist within the same space-time framework. But there was a time when the universe didn't have anything. So where did all this matter come from? While it might seem like everything came from something, scientists also consider the possibility that it all came from nothing. But what does nothing mean in science? To truly answer the question of how something could arise from nothing, we would first need to understand several interpretations of nothing. This is the state where nothing is that the essential building blocks for everything we see are absent. Imagine a universe with no galaxies, stars, planets, or even humans. Everything we know and interact with is made up of tiny subatomic particles. These particles are the building blocks that shape our universe. If we start with a universe full of matter, we can understand how it grows, cools down, and is influenced by gravity to become the universe we see today. We know that stars go through life cycles, creating heavier elements that lead to the birth of new stars, planets, organic compounds, and eventually life. But here are some big scientific questions. How did we end up with a universe dominated by matter, and not one with equal amounts of matter and antimatter? This is one of the biggest mysteries in physics. The universe is made almost entirely of matter, with hardly any antimatter. Every star, planet, and galaxy we've observed is made of matter. So how did we get this surplus of matter? This puzzle is known as baryogenesis, the process of creating an excess of baryons over antibaryons in the early universe. Scientists have many theories, but we still don't have a definitive answer. We don't know why there's more matter than antimatter instead of an equal balance. To truly answer the question of how something could arise from nothing, we need to understand different ideas of what nothing means. Our second interpretation of nothing is the emptiness of vast space. Maybe you think of nothing as truly having no things at all. If that's the case, then the first explanation of nothing with missing building blocks doesn't quite fit, because it still involves something. To really understand this concept of nothingness, let's imagine getting rid of every basic element of matter. That means removing every single particle and every bit of energy. If we could manage to remove all of these, what would remain? Just the vast expanse of empty space. No particles, no matter, no radiation at all. This is what some scientists see as the true scientific meaning of nothingness. Space-time itself, guided by the principles of general relativity, still exists. The speed of light and gravitational constant still retain their values. And most importantly, there's something called zero-point energy. Even in the emptiest space, there's still a tiny amount of energy. Today we see this as dark energy, which is driving the expansion of the universe. But even in this extremely empty scenario, some fundamental aspects still remain. The laws of physics are still there. Quantum fields, like the electromagnetic field, the gravitational field, the Higgs field, and fields related to nuclear forces, still exist. So even without any matter or radiation, this version of nothing still gives rise to an intriguing universe. This leads to the idea of a universe from nothing. It's fascinating to think that even in the absence of everything we see, the universe can still be a dynamic and captivating place. The third interpretation of nothing for scientists is the idea of nothingness as the lowest energy state possible. Right now, our universe has something called zero-point energy. This is a tiny amount of energy that exists everywhere in space. We don't know if this zero-point energy is the absolute lowest energy possible, or if there's an even lower energy state we haven't discovered yet. There's a chance we might be in a false vacuum state, with the true vacuum, or the absolute lowest energy state, either near zero, or perhaps even reaching or surpassing it. If the universe changes from this false vacuum to a true vacuum, it could trigger a catastrophic event called vacuum decay. This would drastically change the universe. Photons, which are particles of light, would get mass. The electromagnetic force would be confined to short distances, and most of the sunlight from the sun wouldn't reach Earth. Thinking of nothingness as the ultimate lowest energy state means imagining a situation where all matter, energy, radiation, and any distortions in space-time are removed. What remains is a state of perfect emptiness, but with the laws of physics still in place. This ultimate low-energy state would make it impossible to create any work, energy, or particles from it. However, some might still see this as something because space, time, and the laws of physics would still exist. In this state, there would still be a backdrop for events to happen, but without any actors or actions. It would be like a play with no characters, storyline, or setting, just an empty stage. Now imagine reaching the universe's true foundational state, whatever that might be. In this state, all matter, energy, and any distortions in space-time would be removed. What would be left is the ultimate material emptiness. This ultimate low-energy state would make it impossible to create any work, energy, or particles from it. However, some might still see this as something because space, time, and the laws of physics would still exist. So our third interpretation of nothing is the ultimate lowest energy state possible for the universe. Even in this state, the framework of space, time, and the laws of physics remain. It's another incredible mystery that keeps scientists exploring and searching for answers. This is the most extreme interpretation of nothing. It's the idea that true nothingness only happens when the entire universe and its governing laws are completely gone. This is a radical idea that goes beyond our usual understanding of reality. Imagine getting rid of everything, including space, time, and even the laws of physics. This kind of nothing is beyond what we can define with physics because it represents an absolute void, a total absence of everything. From a physics standpoint, this idea is challenging. How can something like space-time exist if there's no space or time? How can the laws of physics work if there's no framework for them? This kind of nothing is hard to comprehend and might not have any real-world meaning. Thinking about this ultimate nothingness brings up many questions without clear answers. For instance, how could space and time begin in a place where they don't exist? Is it possible to have something without space, or something starting without time? Imagine an absolute nothingness, a complete void. From a physics perspective, it suggests a state beyond the limits of space and time, from which our universe and its laws might have originated. However, we're not sure if this idea is meaningful or just a product of our imagination. This concept raises many difficult questions. For instance, how can space and time begin in a place or moment where neither exists? Can we even imagine something existing outside the universe without space, or starting without time? Where would the rules that govern particles and their interactions come from? This idea of nothingness, while it seems philosophically complete, might not have any real substance. It could just be a way for us to understand things that are beyond our reality. When scientists talk about nothing, they often assume everyone has the same idea of what nothing means. But that's not always the case. Different people and different contexts can change how we understand nothing. While theories about nothing, they are grounded in scientific principles and observations. The study of the cosmic microwave background radiation, the faint afterglow of the Big Bang, provides insights into the early universe's conditions. Detailed measurements of the CMB have helped for understanding of the universe's age, composition, and structure. Observations of the expansion of the universe, as described by Hubble's law, support the idea that the universe began from a hot, dense state. Additionally, the discovery of dark matter and dark energy, which make up most of the universe's mass-energy content, suggests that our understanding of the universe is still incomplete. The phrase "something from nothing" might mean creating something entirely new, where there was truly nothing before. But not everyone agrees on what nothing really means. In the end, it's important to understand which version of nothing someone is talking about. In everyday language, nothing suggests the absence of anything at all. However, in the context of cosmology, nothing can be much more complex. It can refer to a quantum vacuum, a state with the lowest possible energy where particles and antiparticles constantly pop in and out of existence due to quantum fluctuations. Philosophically, nothing can be even more abstract. Some philosophers argue that true nothingness is an absolute void without any properties or existence. Others suggest that even in a state of nothingness, there must be some form of potentiality or possibility that allows for the emergence of something. None of the evidence from the cosmic microwave background radiation or quantum fluctuations tells us what was there before the Big Bang. One of the most mysterious questions in cosmology is what existed before the Big Bang and what created the singularity that led to it. The Big Bang theory tells us that the universe started from an incredibly dense and hot point called a singularity. Think of a singularity as a point where everything we know about space and time breaks down, including laws of physics. If our usual laws of physics don't apply here, then what are the rules? To understand this, let's start with Albert Einstein's ideas. His theory of relativity changed how we see the universe by linking mass and time. According to his theory, time is not fixed, but changes based on the gravitational fields of objects with significant mass. He showed that massive objects, like Earth, can slow down time. Now, if mass slows down time, imagine what the singularity does, containing all the mass of the universe. It would stop time completely. So according to Einstein, the idea of before the Big Bang doesn't really make sense because time itself didn't exist. The cosmic microwave background radiation is a key piece of evidence. It comes from a time about 380,000 years after the Big Bang, when the universe was cooling down and forming hydrogen atoms. Before this, the universe went through several phases, starting from the Planck epoch to the Grand Unification, inflationary, electroweak, quark, and hadron epochs. Each phase saw different particles and forces evolving into what we know today. When we talk about the universe at such a small scale, quantum mechanics takes over from classical physics. This led scientists like Stephen Hawking to think about how quantum theory could apply to the whole universe. This is where inflationary quantum cosmology comes in. Unlike classical theories that describe the singularity as a point with zero volume, quantum cosmology suggests there's an element of uncertainty. This means we can't pinpoint the exact moment the universe was created, and particles can pop in and out of existence from what we call a vacuum. In physics, a vacuum is not a state of absolute emptiness, but rather a state without particles. According to Heisenberg's uncertainty principle, there's always some level of fluctuation. So a perfect vacuum with zero field values is impossible. This might sound strange, but Einstein's famous equation, E=mc2, helps explain it. The positive energy in stars and galaxies must be balanced by an equal amount of negative energy, like gravity. If the universe's total energy is zero, then it's possible for it to come from nothing. The idea that hundreds of billions of galaxies could come from nothing sounds unbelievable. However, Einstein's famous equation, E=mc2, gives us some clues. According to this equation, all the positive energy in stars, galaxies, and other celestial bodies must be balanced by an equal amount of negative energy, which appears as gravity. In a closed universe, or one that will eventually collapse back onto itself, these positive and negative energies would perfectly cancel each other out, resulting in a net energy of zero for the universe as a whole. Stephen Hawking asked how a universe with zero total energy could come from nothing. He suggested that gravity's negative energy could balance out the positive energy needed to create matter. This makes empty space stable. Physicist Alexander Vilenkin took this idea further, showing that a small energy-filled vacuum could spontaneously appear from nothing and expand into the universe we see today. This means our universe could have started from a state of nothing, where time didn't exist. Another intriguing possibility is the multiverse hypothesis, which suggests that our universe is just one of many universes that exist simultaneously. In this framework, the Big Bang that created our universe might be just one of countless such events occurring within a larger multiverse. In the multiverse scenario, there could be a constant creation of new universes, each with its own set of physical laws and constants. These universes could be born from different processes, such as quantum fluctuations or collisions between higher dimensional membranes in string theory. The existence of a multiverse implies that our universe's beginning was just one event in an endless cycle of creation and destruction. Some theories in physics propose the existence of higher dimensions beyond the familiar three spatial dimensions and one-time dimension. These higher dimensions could play a crucial role in the origin of the universe. String theory, for example, suggests that the fundamental building blocks of the universe are one-dimensional strings, that vibrate in multiple dimensions. In this framework, our universe could be a three-dimensional brain floating in a higher dimensional space. Collisions or interactions between these brains could trigger events like the Big Bang, creating new universes. So what was there before the Big Bang? The theories we've explored suggest that time itself started with the Big Bang, making before a tricky concept. From singularities to quantum fluctuations, these ideas show just how incredible and mysterious our universe really is. The Big Bang theory explains how the universe expanded from a super hot and dense state, but it doesn't tell us what happened before that moment. According to the theory, time, space, matter, and energy all started with the Big Bang. However, some scientists have ideas about what might have been before the Big Bang. One interesting idea is the Big Bounce. This theory suggests that the universe goes through cycles of expanding and contracting. So the Big Bang we know might have been just one of many bounces, with the universe constantly being reborn. Another fascinating idea is the concept of a multiverse. This theory proposes that our universe is just one of many universes, each with its own set of physical laws. In this model, what existed before our Big Bang could have been another universe entirely. These ideas push the limits of our current understanding and venture into the speculative. They rely on advanced concepts in quantum physics and the still theoretical realm of quantum gravity. Scientists are trying to connect the dots between quantum mechanics and general relativity to better understand these possibilities. After the Big Bang, the universe kept expanding and cooling. At first, it was just a soup of tiny particles. As it cooled, these particles came together to form the first atoms, mainly hydrogen and helium. While these theories offer exciting glimpses into what might have been before the Big Bang, they remain largely theoretical, highlighting the deep mystery of our universe's origins. By looking back in time, we can explore the origins of each cosmic structure. Each discovery leads to another question. Where did this come from, and how did it form? These questions continue until we reach a point where the only honest answer is, we don't know, at least not yet. With what we do understand, we then face the intriguing questions. How did all of this come to be? The life we see today is made possible by complex molecules, which originally evolved from the simple atoms listed in the periodic table. These atoms are the fundamental components of all the ordinary matter in our universe. These atoms weren't just there from the universe's beginning. They formed through numerous cycles of stars being born, living, and dying. Each cycle of stellar life contributed to the nuclear reactions that produced these atoms, which were then recycled into newer generations of stars. Without this ongoing process, the creation of planets and the complex chemistry needed for life would not have been possible. To understand how the stars and galaxies we see today came to be, a few key pieces need to fit into place. First, gravity plays a huge role. It pulls together smaller groups of stars and galaxies to form the large galaxies we observe, kickstarting new rounds of star formation. For gravity to do its job, there must be enough mass already clumped together. This is where dark matter comes in. Early in the universe's history, dark matter formed halos that helped keep the newly formed stars from scattering their material back out into space. Besides, the right mix of matter like atoms, dark matter, and radiation is crucial. This mix not only produced the cosmic microwave background, a kind of afterglow from the Big Bang, but also created the light elements during that hot, dense state of the early universe. The growth of galaxies and star clusters depended on initial small differences in density, often called seed fluctuations, which needed to grow under gravity's influence. Finally, there must be processes that initially created these density variations, dark matter, and the first batches of ordinary matter. To grasp how our universe came to be from the chaos of the Big Bang, we need to consider some critical conditions right from the start. For one, the laws of physics, the fabric of space-time, and the essence of matter-energy weren't just there. They had to emerge somehow. Take a closer look at this picture. This is Eugene Cernan, the last astronaut from the Apollo program to walk on the moon. But there's something unusual here. Do you see it? The night sky appears completely empty of stars. In every photo taken during the Apollo missions, the sky looks empty of stars. Despite the universe being filled with trillions of stars, Apollo astronauts reported that they couldn't see a single star from the moon. This absence of stars has sparked numerous conspiracy theories over the years. Some people even claim it's proof that the moon landing was staged. However, the real explanation is far more intriguing and delves deeper than any conspiracy theory could. Why is space so dark and empty? This question was first proposed by astronomer Johannes Kepler in 1610. Our home galaxy, the Milky Way, is incredibly vast, believed to contain between 100 and 400 billion stars. The observable universe alone is estimated to contain trillions of galaxies, each with trillions or sextillions of stars. Given this, astronomers wondered why the sky isn't bright and full of light, considering the countless stars in every direction. Surprisingly, it isn't, and this puzzled astronomers for centuries. Careful study suggests that the sky should be as bright as the surface of the sun. We should be surrounded by a blazing oven of light. Yet, when we look up at night, we mostly see darkness. This puzzle, known as Olbers' paradox, took nearly 300 years to solve. Olbers' paradox came from the steady-state theory. Imagine a universe where everything has always been the same and always stays where there are, including stars, galaxies, everything. This was the core idea behind the steady-state theory, which was once the main explanation of the universe. It said that the universe was infinite, without a beginning or end, uniform in every direction, and did not expand. With this theory in mind, astronomers faced a question: why is the night sky dark? If the universe has always existed and is full of stars, then shouldn't the whole night sky be as bright as the sun? According to the steady-state theory, even the light from the most distant stars should have reached us by now, lighting up the sky with their combined glow. One early explanation suggested that maybe the stars were just too far away to affect our night sky. But this idea didn't work with the steady-state model. If the universe is infinitely old, there would have been plenty of time for the light from any star to reach Earth, no matter if that star lies at the edge of the universe. This light should fill the sky, leaving no dark patches. Johannes Kepler had a different idea to solve the Olbers' paradox, which went against the steady-state theory. He suggested that the universe wasn't infinite after all. Instead, he proposed that stars only spread out to a certain limit, and beyond that, there was just empty space. This idea was interesting, but it raised big questions. How far does this space with stars go, and what's beyond that edge? Kepler's idea of a limited universe also had its own problems. If the universe had a boundary, the combined gravity of all the stars and planets could potentially pull everything back together, causing the universe to collapse. Because of these challenges, most astronomers kept believing that the universe was infinite. This meant that the paradox and the idea of a steady universe were left unresolved for nearly 200 years. Then, in 1823, a famous German astronomer named Heinrich Olber brought attention back to this old question, asking again, why is the night sky dark? Since then, Olber's name has become closely linked with the paradox. In his time, people still believed the universe was unchanging. Olbers suggested a simple idea. If the universe is infinite, it would be full of dust and rocks. These particles could block the light from distant stars, making them look dimmer to us. This cosmic dust and rocks absorb and block starlight as they move through space. Today, many people still think this way, comparing it to how clouds block sunlight and obscure the sky. Just like clouds, cosmic dust and rocks can hide the light from stars. However, Olber's explanation wasn't complete. Over time, the dust and rocks blocking the light would heat up and start to glow themselves. This means the universe would still be filled with light, just like before. The dust and rocks only temporarily hide the light from the stars before releasing it again, so the overall amount of light reaching us would still be the same. So what really solves this paradox? It took another 100 years to find the real answer. In 1929, Edwin Hubble used his powerful telescope, hoping to find signs of the universe shrinking. This would support the idea of a finite universe, like Kepler suggested. But instead, Hubble found that galaxies were moving away from us, and the farther a galaxy was, the faster it seemed to be moving away. This showed that the universe was not staying the same or collapsing, but was actually expanding. This discovery led to a new question. What does an expanding universe mean for its beginning? Scientists now think the universe started as something incredibly tiny and dense. It then expanded very quickly, a process called cosmic inflation. As it expanded, it cooled down, and eventually stars and galaxies began to form. This understanding helped develop what we now call the Big Bang Theory. Scientists believe this all started about 13.8 billion years ago, and it's currently our best explanation of how our universe began. When we use telescopes to look beyond the earliest stars, we see a special type of light. This isn't light from stars, but light that's left over from the Big Bang. It forms a kind of background glow beyond where the stars are. However, the Big Bang Theory brings up a new issue. It suggests that the universe used to be much brighter, especially during a time called the Recombination Era. Back then, the whole sky would have been as bright as the sun because the universe was very hot. This means that the background glow from the Big Bang, known as cosmic background radiation, should be very bright. According to Olber's paradox, this bright background should make it hard for us to see any faint stars in the night sky. Today, most scientists agree that the universe is about 13.8 billion years old. When we look at light that's 13.8 billion years old, we don't see stars not because the light hasn't reached us, but because we are looking back to a time before stars even existed. The farther we look into space, the further back in time we are seeing, until we reach what seems like the edge of the universe. This isn't a real edge, but rather the oldest light we can see, known as the cosmic microwave background. It's the leftover glow from the Big Bang. Since the Big Bang happened 13.8 billion years ago, the universe has been following three main rules as it grows and changes. First, at the very beginning, the universe was extremely tiny, very dense, and super hot. Second, just a tiny fraction of a second after it started, the universe began to grow bigger and cooler. Third, and this is really important, the universe will keep expanding and cooling down. Astronomers believe this will go on until the universe becomes so cold that all heat disappears. They call this the heat death of the universe, sometimes also known as the Big Freeze. In this future scenario, the universe has expanded so much that it has cooled down completely, and all heat energy has gone away. All these rules show us that our universe has been getting bigger for the last 13.8 billion years. When the universe started, it was filled with very bright and hot light. As the universe has expanded, this light has been stretched out. This stretching has turned the light into longer wavelengths, which means it's cooler and not as bright as before. This is what we call the redshift effect. It's the reason why the cosmic background radiation isn't extremely bright. Thanks to the discovery of redshift and cosmic background radiation, we now know that the Big Bang and the expansion of the universe solve Olber's paradox. The universe started from a single point and quickly grew during the Big Bang. Over billions of years, it has cooled down. Because the universe isn't infinitely old, there's a limit to how far we can see into space. The redshift effect also makes the light from faraway objects appear dimmer. These factors combine to give us the dark night sky we see today. The fact that the night sky is dark shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe started with the Big Bang and has been expanding ever since. The night sky is like a quiet reminder of how the universe began as a very hot and dense place. This insight helps solve Olber's paradox and also makes us appreciate just how amazing and complex the universe really is. The question of the age of the universe is a fundamental one in cosmology and astronomy. The most widely accepted explanation for the origin of the universe is the Big Bang theory. According to this theory, the universe began as an incredibly hot and dense point, approximately 13.8 billion years ago. This singularity contained all the matter and energy that would eventually form everything we see today. The universe has been expanding ever since, cooling down and forming structures like galaxies, stars, and planets. To determine the age of the universe, scientists use several methods, including studying the cosmic microwave background radiation, observing the expansion rate of the universe, and analyzing the oldest known objects within the universe. One of the most important pieces of evidence for determining the age of the universe is the CMB, discovered in 1965 by Arno Penzias and Robert Wilson. The CMB is the afterglow of the Big Bang. It is the leftover heat from the early universe, now cooled and stretched to microwave wavelengths because the universe is expanding. The Planck satellite by the European Space Agency has provided the most accurate measurements of the CMB to date. The data from Planck has allowed scientists to determine the age of the universe to be approximately 13.8 billion years. The CMB gives us a perfect picture of the universe when it was just 380,000 years old. By studying tiny variations in the CMB, scientists can learn about the universe's early conditions and how it evolved. These variations tell us about the distribution of matter and energy in the early universe, helping us estimate its age. Another method for determining the age of the universe involves observing its expansion. In the 1920s, astronomer Edwin Hubble discovered that galaxies are moving away from us. The farther away a galaxy is, the faster it appears to move. This relationship is known as Hubble's law. By measuring the Hubble constant, scientists can estimate the time since the Big Bang, giving us an estimate of the universe's age. The Hubble constant is a measure of the rate at which the universe is expanding. By determining the Hubble constant, scientists can estimate how long the universe has been expanding since the Big Bang. This involves measuring the redshift of distant galaxies and the distances to these galaxies using various methods, such as observing Cepheid variable stars and supernovae. However, determining the exact value of the Hubble constant has been challenging. Different methods of measurement have yielded slightly different values, leading to what is known as the Hubble tension. Despite this discrepancy, the average value of the Hubble constant, combined with other cosmological data, supports the age of the universe being around 13.8 billion years. Over the years, different methods have been used to measure the Hubble constant, including observing Cepheid stars and studying the CMB. These methods have consistently supported the Big Bang theory and our estimate of the universe's age. Stars also provide valuable clues about the age of the universe. By studying the life cycles of stars, scientists can estimate the ages of the oldest star clusters. One important type of star cluster for this purpose is globular clusters. White dwarf stars, which are the remnants of stars that have exhausted their nuclear fuel, also provide valuable age estimates. By analyzing the cooling rates of white dwarf stars in globular clusters, scientists can determine how long these stars have been cooling and thus their ages. By analyzing the light from these stars and comparing it to models of how stars evolve, scientists can estimate the age of the clusters. Since globular clusters formed shortly after the Big Bang, their ages provide a lower limit for the age of the universe. The oldest globular clusters and white dwarf stars have been found to be around 13 billion years old. Since these objects must have formed after the Big Bang, their ages provide a lower limit on the age of the universe, supporting the estimate of 13.8 billion years. Another method for determining the age of the universe involves radioactive decay. Certain elements, like uranium and thorium, decay at known rates. By measuring the ratios of these elements in old stars and meteorites, scientists can estimate the time that has passed since these elements were formed. This technique, called radioactive dating, has provided age estimates consistent with other methods, supporting the idea that the universe is around 13.8 billion years old. Gravitational waves, ripples in space-time caused by violent cosmic events, offer another way to study the universe's history. First detected in 2015 by the LIGO and Virgo observatories, gravitational waves provide a new way to measure the Hubble constant and the age of the universe. By observing the mergers of neutron stars and black holes, scientists can use gravitational waves to estimate distances and the expansion rate of the universe. This new field of gravitational wave cosmology promises to provide even more precise estimates of the universe's age. According to general relativity, our universe has specific characteristics. It is uniformly dense at large scales, has consistent laws and properties, and the Big Bang occurred everywhere at once. These characteristics create a unique link between the universe's age and its history of expansion. To determine this, we rely on various observations. These include direct measurements of the brightness and distance of celestial objects, which help us build the cosmic distance ladder. We also use observations of large-scale structures, galaxy clusters, and baryon acoustic oscillations, as well as fluctuations in the cosmic microwave background, which offers a snapshot of the universe when it was just 380,000 years old. To summarize the age of the universe, scientists use several methods. These include studying the cosmic microwave background, observing redshifts of distant galaxies, analyzing the life cycles of stars in globular clusters, and exploring the effects of dark matter and dark energy. Each method provides valuable information, and together they give us a detailed understanding of the universe's age and evolution. For years, humans have wondered about the shape of the Earth. Is it flat, round, rectangular, or like a horse's saddle? Today, we know that Earth is roughly a sphere. But have you ever thought about the shape of the universe? Scientists have discovered that the universe is expanding infinitely and not slowing down, but its shape is still debated. There are three possible shapes: flat like a sheet of paper, closed like a ball, or open like a horse's saddle. These shapes are not just theoretical ideas, they have significant implications for the universe's future. They can tell us a lot about its past and what might happen next. Will the universe keep expanding forever, start to contract, or is it infinite and limitless? Let's explore what these different shapes mean for the fate of the cosmos. The overall shape of the universe depends on two main factors: its density and the rate of its expansion. So is the universe closed, open, or flat? About 2/3 of the universe consists of dark energy, and just over a quarter is dark matter. The rest is regular stuff we know, like planets and stars. When scientists talk about the density of the universe, they mean how much matter and energy is packed into a given space. If the universe has enough density for gravity to balance its expansion, it will take on a spherical shape known as a closed universe. A closed universe would be finite, but without any boundaries, meaning you could travel endlessly without ever hitting an edge. On the other hand, If the universe doesn't have enough density to stop its expansion, it will be saddle-shaped, known as an open universe. However, the most reliable scientific data suggests that the universe is flat. In a flat universe, the density is just right, allowing it to expand in all directions without any curvature. What does it mean when we say the universe is flat? This flatness isn't like a two-dimensional surface we see every day. Instead, imagine you're in one corner of a square room. Walk 10 feet to the next corner along the wall, then make a 90-degree turn. Walk another 10 feet, make another 90-degree turn, and do this 2 more times. You'll end up back where you started, forming a square. This follows the Euclidean geometry we learned in school. Now, if you add an extra dimension to this concept, you get a flat universe. In a flat universe, the geometry follows the rules of Euclidean geometry. This means that parallel lines never intersect, and the angles of a triangle add up to 180 degrees. A flat universe can be visualized as a two-dimensional plane that extends infinitely in all directions. A flat universe suggests that the density of matter and energy is exactly equal to the critical density. The critical density is the precise amount of matter and energy needed to make the universe flat. Now, let's consider a positively curved or closed universe. Imagine starting at the equator on Earth and walking to the North Pole. If you turn 90 degrees and walk back to the equator, turn another 90 degrees and return to your starting point, you'll notice that in a closed universe, you would only need 3 turns instead of 4. To make it even simpler, picture 2 rockets flying side by side. In a flat universe, they would stay parallel forever. In a closed universe, their paths would eventually curve and meet again. In an open universe, they would drift apart and never meet again. One important clue about the shape of the universe comes from the cosmic microwave background, the leftover heat from the Big Bang. Scientists have studied the temperature variations in the CMB and found almost no curvature, supporting the idea of a flat universe. However, in 2019, a study suggested that CMB measurements might indicate a closed universe. This was based on the bending of CMB light due to gravity. The observed amount of bending was higher than expected, and a closed universe could explain this. But the team conducting the measurements didn't think this was a big deal. Some experts believe this could just be a random anomaly in the data. Still, these findings are worth noting. It doesn't directly prove that the universe is closed, but it suggests we might be missing something important. Some researchers even call it a cosmological crisis. If the universe were closed, it would conflict with other data, making it hard to accept. If proven true, the idea of a closed universe would overturn years of established research. However, there's no other evidence questioning the prevailing view that the universe is flat. Other CMB measurements and data from telescopes support a flat universe. Additional data, like patterns left on galaxies by ancient sound waves, also back up the flatness hypothesis. Given the overwhelming evidence for a flat universe, most scientists remain skeptical of a single contradictory finding. While the study suggesting a closed universe is interesting, other data consistently supports a flat universe. Recent research combining multiple datasets found no deviation from flatness, suggesting the observed anomaly could be a statistical fluctuation. Other studies have reached similar conclusions, indicating there's no need to revise the current cosmological model. For now, it seems the universe behaves like a 3-dimensional sheet of paper. While not everyone is fully convinced it's definitely flat, that's how it appears based on current observations. It's important to remember that our view is limited to the observable universe, so there might be aspects we're not aware of. If the universe does have curvature, it would have to be so immense that the 93 billion light-years we can observe aren't enough to detect it. To draw an analogy, it's like standing in a foggy field. only able to see a small, flat area, while the true shape of the land remains hidden beyond the fog. When we say the universe is flat, we mean that the part we can observe looks like a flat three-dimensional space. The most widely accepted explanation for the origin of the universe is the Big Bang theory. According to this theory, the universe began approximately 13.8 billion years ago from an incredibly hot and dense state, often described as a singularity. This singularity expanded rapidly, giving rise to the universe as we know it. One of the fundamental aspects of the Big Bang theory is that the expansion of the universe is uniform and isotropic, meaning it looks the same in all directions and has no preferred center. This expansion is often compared to the surface of an inflating balloon, where every point on the surface moves away from every other point. Just as there is no center on the surface of a balloon, scientists believe there is no central point in the universe from which everything is expanding. To understand why the universe has no center, we need to consider the cosmological principle. This principle states that the universe is homogeneous and isotropic on large scales. Homogeneity means that the universe has the same composition and properties everywhere, while isotropy means that the universe looks the same in every direction. The cosmological principle implies that there is no special location in the universe that can be considered its center. Instead, every point in the universe can be viewed as the center of its own observable universe. This principle is supported by observations of the cosmic microwave background radiation, which show a uniform and isotropic distribution of radiation left over from the Big Bang. When we talk about the universe, it's important to differentiate between the observable universe and the entire universe. The observable universe is the region of the universe that we can see from Earth, limited by the speed of light and the age of the universe. Because light takes time to travel, we can only observe objects whose light has had time to reach us since the Big Bang. The observable universe has a finite size, with a radius of about 46.5 billion light-years. However, this does not imply a center in the traditional sense. The observable universe is centered on the observer, meaning that every point in the universe has its own observable universe centered around it. The expansion of the universe is not like an explosion from a central point into pre-existing space. Instead, it is the expansion of space itself. This concept is described by the metric expansion of space, where the distances between points in the universe increase over time. This expansion is uniform and occurs everywhere simultaneously. A useful analogy is to imagine a loaf of raisin bread dough rising. As the dough expands, the raisins move away from each other. There is no single center of expansion within the dough. Instead, every raisin sees the others moving away from it. Similarly, in the universe, every galaxy sees other galaxies moving away due to the expansion of space. One of the key pieces of evidence for the expanding universe is the redshift of light from distant galaxies. As the universe expands, the light from distant galaxies is stretched, causing it to shift towards the red end of the spectrum. This redshift is proportional to the distance of the galaxy, meaning that more distant galaxies are receding faster. Edwin Hubble's observation of the redshift in the 1920s provided strong evidence for the expanding universe and helped establish the Big Bang theory. The uniformity of redshift measurements supports the idea that the expansion is isotropic and that there is no central point from which the universe is expanding. Current cosmological models suggest that the universe is either infinite and unbounded or finite but unbounded. An infinite universe extends infinitely in all directions, while a finite but unbounded universe is closed and has no edges, much like the surface of a sphere. In either case, there is no central point or edge to the universe. If the universe is infinite, every point within it is essentially the center of its own observable universe. If the universe is finite but unbounded, traveling in one direction long enough, would eventually bring you back to your starting point, similar to circumnavigating the Earth. The concept of a universe without a center challenges our intuitive understanding of space and location. Throughout history, humans have often sought a central point or a privileged position in the cosmos. The shift to a heliocentric model of the solar system during the Renaissance was a significant step in changing this perspective. The realization that our galaxy is one of billions in an expanding universe further decentralizes our place in the cosmos. Philosophically, the lack of a center in the universe emphasizes the idea of a uniform and interconnected cosmos. It suggests that no single location is more significant than any other, aligning with the cosmological principle of homogeneity and isotropy. Some theories in modern cosmology propose the existence of a multiverse, a collection of multiple universes that exist simultaneously. In the multiverse scenario, our universe is just one of many, each with its own laws of physics and constants. If the multiverse exists, the concept of a center becomes even more abstract, as there would be no central point in the multiverse as a whole. To answer the question about what exists outside the edge of the universe, first, it's important to differentiate between the observable universe and the entire universe. The observable universe is the region of the universe that we can see from Earth, limited by the speed of light and the age of the universe. Because light takes time to travel, we can only observe objects whose light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. Cosmologists estimate that the oldest photons we can observe have traveled between 45 and 47 billion light-years from the Big Bang, which means that the observable universe has a radius of about 46.5 billion light-years. This is due to the expansion of the universe, which has caused distant objects to move away from us, making the observable universe much larger than 13.8 billion light-years. Moreover, it's concluded that the diameter of the observable universe is about 93 billion light-years, give or take. This observable universe includes everything visible to us, from the smallest particles, like quarks, to the largest structures like quasars, stars, planets, nebulae, and black holes. It's important to note that the observable universe is limited to the light that has reached us. The concept of the edge of the universe often refers to the limit of the observable universe. However, this edge is not a physical boundary, but rather the limit of what we can see or study. Beyond this observable limit, the universe continues to exist, but we cannot observe it directly because the light from those regions has not yet reached us. The universe is believed to be much larger than the observable portion and possibly infinite. If the universe is infinite, it extends endlessly beyond the observable edge. In this case, asking what exists outside the edge of the universe becomes meaningless, because there is no edge, only more universe. But how can the observable universe be 93 billion light-years across if the universe itself is only about 13.8 billion years old? This seeming contradiction is resolved by understanding a fundamental concept in physics. According to the theory of special relativity, objects close to each other cannot exceed the speed of light relative to each other. However, this limit doesn't apply to distant objects, particularly when the space between them is expanding. It's not that these objects are moving through space faster than light, rather, the space itself is expanding, causing them to recede from each other at high speeds. To reach the edge of the observable universe, one would need to surpass the speed of light, a feat considered impossible by most physicists, or find a way around the constraints of space-time, perhaps through theoretical constructs like wormholes or warp drives, though these too are deemed highly speculative. According to the concept of cosmic inflation, the universe could be at least 10 to the power of 23 times larger than what we can observe. What lies beyond the observable universe remains a mystery, as it falls outside our capacity to observe. Nonetheless, various theories speculate on what might exist in these unexplored regions. The first theory is simple but surprising. Astronomers think that the space beyond what we can see might just be a continuous stretch of cosmic features similar to those within our observable universe. It makes sense to assume that the universe beyond our sight wouldn't be drastically different from what we can observe. It's difficult to picture a universe that just ends abruptly, as if there's a giant wall marking its boundary. So the idea that the universe could be infinite is somewhat natural. But infinite means that beyond what we see, there could be endless stars, planets, and even every possible scenario you can imagine. If the universe really is infinite, following this idea to its fullest extent means that somewhere out there could be another person who looks exactly like you and lives a life remarkably similar to yours. There might also be versions of you who are slightly different. Maybe one is a bit shorter, another might have passed away a few years ago, or one might be missing a finger. It's possible that this other version of you is watching this video right now, maybe even picking their nose, just as you might be. It's a wild idea, but that's how the concept of infinity works. Another theory called dark flow came about in 2008 when astronomers observed galaxy clusters moving in the same direction incredibly fast, over 2 million miles per hour. This might be caused by huge unknown structures beyond what we can see pulling these galaxies with their gravity. These structures could be massive clusters of matter and energy, or unusual space-time distortions that could even connect to other universes. We really don't know what these massive entities could be. Although some recent studies have tried to debunk the dark flow theory, it's still being debated. There's also the idea of a multiverse, where our universe is just one bubble in a huge sea of other universe bubbles. This theory suggests that these universes can interact, and the gravitational pull between them could cause collisions, potentially leading to events similar to our own Big Bang. These ideas are just a few of the popular theories about what might lie beyond the part of the universe we can see. The true nature of what's out there remains one of the biggest mysteries in cosmology, driving continued research and discovery to learn more about our vast universe. Some theories even suggest the existence of extra dimensions beyond the 3 spatial and 1 temporal dimensions we experience daily. For example, string theory proposes additional dimensions that are too small for us to detect. If these extra dimensions do exist, they could contain entire universes with their own sets of physical laws and constants, potentially offering insights into the structure and limits of our universe. There's also the cyclic universe theory, which suggests the universe goes through endless cycles of expansion and contraction. According to this theory, the universe expands to a certain point, then gravity pulls everything back into a dense state, leading to a big crunch that sets off another Big Bang. This continuous cycle of creation and destruction suggests that the universe's edge might just be a transition point in an eternal sequence. The universe is expanding, and this expansion affects our ability to observe distant regions. The expansion is driven by dark energy, a mysterious force that accelerates the rate of expansion. As the universe expands, distant galaxies move away from us, and the light from these galaxies is redshift to longer wavelengths. The expansion of the universe creates a cosmic horizon, a boundary beyond which we cannot see. This horizon is determined by the distance that light has traveled since the Big Bang. As the universe continues to expand, the cosmic horizon will change, potentially revealing new regions of space that were previously beyond our observational reach. This horizon represents the furthest distance light has traveled to us since the universe began. Anything beyond this horizon remains out of our reach, locked away by the finite speed of light and the age of the universe. To fully grasp what might exist outside the universe, we need to consider the nature of space and time. According to general relativity, space and time are intertwined in a four-dimensional continuum known as space-time. The curvature of space-time is determined by the distribution of mass and energy in the universe. If the universe is finite and unbounded, the curvature of space-time could create a closed, self-contained cosmos with no external space or time. In this model, asking what exists outside the universe is like asking what lies north of the North Pole. It is a question that may not have a meaningful answer within the context of our physical laws. The universe is a vast and mysterious place, filled with galaxies, stars, planets, and countless other celestial objects. However, one of the most puzzling discoveries in modern cosmology is that the majority of the universe, about 95%, is missing. Matter, which makes up about 5% of the universe, includes the atoms and particles that form stars and galaxies. Dark matter, accounting for about 27% of the universe, remains invisible and is detectable only through its gravitational effects on visible matter. Dark matter acts as a cosmic framework, guiding the structure and formation of galaxies. The concept of dark matter was first proposed in the early 20th century when astronomers noticed inconsistency between the observed mass of galaxies and the mass inferred from their gravitational effects. In the 1930s, Fritz Zwicky observed that galaxies in the Coma cluster were moving much faster than expected based on the visible mass alone. He hypothesized the presence of dark matter that provided additional gravitational force. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Although it does not interact with electromagnetic forces, dark matter exerts gravitational influence on visible matter, radiation, and the structure of the universe. The most dominant yet difficult to understand component is dark energy, making up approximately 68% of the universe. This mysterious force drives the accelerated expansion of the universe, acting against the gravitational pull of matter. Together, these components form the fabric of the cosmos, from the smallest particles to the largest galactic structures. We don't know exactly what dark matter and dark energy are, but we're fairly confident they're real. So, what's known? Dark matter is essential for galaxies to form. When scientists analyzed the structure of the universe, they realized there's not enough regular matter. The gravitational force of visible matter isn't strong enough to create galaxies or complex systems. Without dark matter, stars would likely be scattered randomly rather than forming the magnificent galaxies we observe. This suggests that dark matter acts like glue. This mysterious component, which neither emits or reflects light, is known as dark matter. Though invisible, dark matter can be indirectly observed. Areas with high concentrations of dark matter bend light that passes close by, a phenomenon known as gravitational lensing. This bending effect acts as a clue, revealing the presence of dark matter through its gravitational interactions. First, we know that dark matter isn't just ordinary matter without stars. Ordinary matter emits detectable particles, making it visible to our instruments. If dark matter was simply ordinary matter, we would have already observed it. It's also not antimatter. Antimatter emits unique gamma rays when it reacts with regular matter. If dark matter were antimatter, these gamma rays would provide a clear signal, which we have not detected. Dark matter isn't made of black holes either. Black holes are compact objects that have a strong impact on their surroundings, while dark matter seems to be spread out through the cosmos. The gravitational effects of black holes are also different from what we observe with dark matter. Scientists are exploring various ideas and conducting experiments to uncover the true nature of dark matter. Even the precise 15-month survey of the cosmos by the European Space Agency's Planck spacecraft was only able to detect less than 5% of the total observable universe. For years, scientists have been trying to solve the mystery of dark matter. They have been able to infer the existence of dark matter only from the gravitational effect it seems to have on visible matter. Renowned British physicist Brian Cox explains that dark matter could be some kind of particle that we are currently unaware of. But how do we find dark matter? Scientists are searching for this mysterious dark matter using the world's largest physics experiment at CERN in Switzerland, the Large Hadron Collider. Instead of trying to find it, they're trying to make some from scratch. They do this by smashing together known particles at very high speeds to create huge amounts of energy in these impacts. This energy might produce particles of dark matter. When the protons collide, they usually create new particles, but these are often low-mass particles. However, very rarely, these collisions produce much heavier particles, and those are the ones scientists are looking for. So the search for dark matter continues in underground labs, at CERN, and by observing the night sky. Scientists believe they're getting closer to discovering what it's made of. The most popular candidates for dark matter are called WIMPs, or weakly interacting massive particles. These particles are hypothesized to interact very weakly with normal matter, making them incredibly hard to detect. The underground detectors aim to observe these rare interactions, providing clues to the nature of dark matter. One of the most fascinating pieces of evidence comes from gravitational lensing. This phenomenon occurs when light from distant objects, like galaxies or quasars, is bent around a massive object, such as a galaxy cluster due to gravity. The amount of bending observed can reveal the presence of dark matter, as it contributes to the overall gravitational field. Astronomers also play a key role in the search for dark matter. By observing the night sky, they study the behavior of galaxies and galaxy clusters. The way these massive structures move and interact provides indirect evidence of dark matter. For example, the rotation curves of galaxies show how fast stars orbit the center. The gravitational effects we observe suggest there's much more mass present, and that's attributed to dark matter. While we haven't yet directly detected dark matter, each experiment brings us closer to understanding this mysterious component of the universe. Dark energy is even more mysterious than dark matter. It is a form of energy that we can't exactly detect or measure, but we can see its effects. Unlike dark matter, which clumps together due to gravity, dark energy is evenly distributed throughout space. In 1929, astronomer Edwin Hubble made a groundbreaking discovery. He studied how light wavelengths from distant galaxies shift towards the red end of the spectrum as they travel through space. This phenomenon, known as redshift, revealed a startling truth. Hubble found that fainter, more distant galaxies showed more redshift, while closer ones exhibited less. He concluded that this redshift was because the universe is expanding. As light wavelengths stretch, they shift towards the red end of the spectrum, indicating that space itself is growing. Recent findings have taken Hubble's discovery even further. The universe's expansion is not just continuing, it's accelerating. Previously, scientists believed that gravity would slow down or even reverse this expansion. Now, scientists have found that this rapid expansion rate is because of dark energy, which is driving the universe apart at an ever-increasing rate. Space itself doesn't change its properties as it expands. New space is constantly being created everywhere. Galaxies remain tightly bound clusters held together by gravity, so we don't experience this expansion in our daily lives. But we see it everywhere in the universe. Wherever there's empty space, more is forming every second. So what is dark energy? It seems to be some kind of energy in empty space, stronger than anything else we know and constantly increasing. Empty space holds more energy than everything else in the universe combined. This mysterious force is pushing galaxies apart, accelerating the expansion of the universe. Dark energy remains one of the greatest mysteries in cosmology. While we can't detect or measure it directly, its influence on the universe is undeniable. As we continue to explore and study the cosmos, we hope to unravel the secrets of this enigmatic force, bringing us closer to understanding the true nature of our ever-expanding universe. The discovery that this expansion is speeding up suggests that a mysterious force called dark energy is at work. Understanding dark energy is one of the biggest challenges in cosmology today. Considering the vastness of the universe, it's intriguing to ponder our significance within it. Are we unique in the cosmic scheme, or just one of many life forms potentially scattered throughout the cosmos? This leads to the question, was the universe specifically designed with us in mind? This idea is captured by the anthropic principle, which suggests that the universe's fundamental laws and constants seem precisely calibrated to support life, especially intelligent life like humans. For instance, the exact values of gravitational force, the strength of electromagnetic interactions, and the characteristics of atoms are essential for life. Any slight variations in these constants could make life as we know it impossible. So, does this precision in the universe's design suggest it was crafted specifically for us? Some argue that the exact conditions enabling life are too precisely matched to be mere coincidence, hinting at intentional creation. Conversely, others maintain that this fine-tuning is merely the outcome of natural processes and random chance. They point out that in an immensely vast universe, it's entirely plausible for at least one planet, such as Earth, to naturally develop the perfect conditions for life. The multiverse theory adds another layer to this discussion. It proposes that our universe is just one among potentially countless others, each governed by its own set of physical laws and constants. In this vast multiverse, only a select few universes might harbor conditions conducive to life. If this theory holds true, our universe isn't particularly special. It's simply one of the few where conditions align perfectly for life, making the concept of fine-tuning less extraordinary. Exploring extraterrestrial life also influences this debate. Discovering life beyond Earth, whether microbial life on Mars, in the hidden oceans of moons like Europa and Enceladus, or on distant exoplanets, would imply that life is not an Earth-exclusive phenomenon, but a widespread occurrence wherever conditions are favorable. Such discoveries could dramatically shift our understanding of life's rarity in the universe. Beyond the scientific realm, philosophical views also shape our understanding of the universe. Some find solace in believing the universe has a deliberate purpose, while others appreciate the beauty in its randomness and endless possibilities. Regardless of the universe's intent, our innate curiosity and drive to explore are quintessential human traits. Delving into these profound questions not only propels scientific advancement, but also deepens our grasp of the cosmos. Science portrays the universe as vast and seemingly indifferent, which might make us feel trivial. Yet some contend that we might still occupy a central role in the cosmos due to the finely tuned laws of physics that make life possible. For example, the specific strength of the electromagnetic force is vital for stars to produce carbon, a fundamental building block of life. Even the energy in the vacuum of space appears to be calibrated for the rise of intelligent life. This apparent fine-tuning has given rise to various interpretations of the anthropic principle. One perspective posits that the universe was deliberately designed with us in mind, possibly by an intelligent entity. Another concept, the life principle, suggests that life is an inherent characteristic of the universe. However, these views are not broadly endorsed in the scientific community. An alternative philosophical interpretation of the anthropic principle is that the universe exists because we are here to observe it. A more pragmatic view holds that the universe appears tailored for our existence simply because we live in a region that supports life. This might be explained by the existence of multiple universes, each governed by different physical laws with ours being one of the few capable of supporting life. We live in a world with 3 dimensions: up and down, left and right, and forward and backward. These are the directions in which we can move. Time is another dimension we experience, moving from the past to the future. Together, these make up what we call space-time. In physics, dimensions are like different directions you can move. You can think of them as lines on a graph. Normally, we only experience 3 dimensions. But what if there are more dimensions that we can't see? Theories like string theory and M theory from theoretical physics suggest there might be extra dimensions. According to string theory, the smallest parts of our universe are not points, but tiny vibrating loops of energy called strings. The mathematics behind string theory suggests there need to be 10 or 11 dimensions for everything to work out. String theory tries to explain all of nature's forces, gravity, electromagnetism, and the nuclear forces by saying everything is made up of these strings. The different ways the strings vibrate make up different particles. Why don't we see these extra dimensions? They might be incredibly small and tightly folded, making them impossible to detect with our current tools. For example, imagine an ant on a tightrope. To the ant, the rope looks like a line because it can't see the width. Similarly, these extra dimensions are there, but they are too small or hidden for us to notice. If these higher dimensions do exist, they could help us understand some of physics' biggest questions, like why gravity is much weaker compared to other forces. Maybe gravity spreads out into these extra dimensions, which would explain why it seems weaker in our 3-dimensional world. Higher dimensions might help us understand the basic nature of particles and forces better. They could link all the different natural forces into one big framework, which could lead to new technologies and a deeper knowledge of the universe. Scientists are trying to find evidence of these higher dimensions. One way they do this is by looking for small changes in gravity's behavior at very tiny scales. If higher dimensions are real, they could cause slight unusual effects in how gravity works, which we might spot in lab experiments. Another method involves using high-energy particle collisions, like those at the Large Hadron Collider. These experiments smash particles together at high speeds, and if any particles disappear into higher dimensions, it could hint that these dimensions exist. There are also other interesting ideas about higher dimensions. For example, some theories suggest that our universe might be a 3-dimensional brain, floating in a space with more dimensions. In this idea of a brain world, our universe could be just one of many parallel universes, each existing as a separate brain in a space with more dimensions. This raises exciting possibilities about how these universes might affect each other, such as through gravity or by exchanging particles. Another idea related to higher dimensions is the multiverse theory. This theory suggests that our universe is just one bubble in a vast sea of other universes, each in a higher dimensional space. These different universes could have their own sets of physical rules and might even interact with each other. For example, when these universes collide, it could create a huge explosion similar to the Big Bang that started our universe. While the concept of higher dimensions is fascinating, it's still just a theory. One of the biggest hurdles is that these dimensions are not something we can currently see or measure directly. To detect them, we would need extremely high energy levels or very precise measurements that are beyond our current capabilities. Mathematics is essential in helping us understand the concept of higher dimensions. Many theories suggesting the existence of these extra dimensions heavily depend on complex mathematical ideas from geometry, topology, and algebra. These branches of math help us picture and make sense of spaces that go beyond our usual 3-dimensional understanding. Mathematicians and physicists collaborate to create models that hypothesize how these higher dimensions might affect what we can observe in the universe. These models are then put to the test through various experiments and observations. Quantum mechanics, which looks at how particles behave at incredibly small scales, could also be impacted by higher dimensions. The weird and often puzzling behaviors we see in quantum mechanics might be due to interactions happening in spaces with more than 3 dimensions. So are there really higher dimensions in the universe? While we don't have solid proof yet, the possibility of higher dimensions is a thrilling and active field of research in theoretical physics. If these dimensions do exist, they could dramatically change our understanding of the universe and reveal new secrets about the nature of reality. Studying the entire universe is one of the most ambitious and exciting endeavors in science. The universe is vast, stretching billions of light-years across, filled with galaxies, stars, planets, and countless other celestial objects. To understand the universe's structure, origins, and ultimate fate, scientists use a variety of methods and tools. Let's explore how we study the universe, from the telescopes that capture its light to the theories that explain its mysteries. Telescopes are the primary tools astronomers use to study the universe. They allow us to observe distant objects by collecting and magnifying their light. There are several types of telescopes, each designed to capture different wavelengths of light and other forms of electromagnetic radiation. Think of the universe like a pie chart, with different slices representing different components. First, we have normal matter, which makes up only 5% of the universe. This includes atoms that form stars, planets, and everything we see around us. Next is dark matter, an unknown type of particle that accounts for about 25% of the universe. Scientists calculate the amount of dark matter by observing tiny temperature variations in the cosmic microwave background. These calculations match what we observe from the movements of stars and galaxies. The CMB comes from a time when the universe had cooled enough to release photons from the hot plasma that trapped them for hundreds of thousands of years after the Big Bang, confirming that dark matter was present in the early universe. Atoms, or normal matter, make up only 1/6 of the universe's total mass. Then there's dark energy, a mysterious force responsible for the rapid expansion of the universe. It makes up 70% of the universe's total matter and energy. We also have the optical layer, which tells us how much the universe absorbs and scatters light, particularly photons. This layer helps us understand the complex processes behind the birth and explosive end of the first stars and the formation of the earliest galaxies. When these early stars and galaxies formed, they emitted intense radiation that broke hydrogen atoms into protons and electrons. This event, known as reionization, caused about 5 to 8% of the CMB photons, released during the decoupling era, to scatter once more. Imagine it as a light mist appearing in a previously clear universe, slightly reducing our visibility. To measure this depth of the universe, scientists study the polarization of the CMB. This gives us clues about the early stages of the universe and helps us piece together the story of how the first stars and galaxies came to be. Exploring the mysteries of the universe, we encounter the concept of polarization, which, along with intensity and wavelength, is one of the 3 attributes of a light wave. Some of the fluctuations and the formation of structures in the universe are described by the primordial power spectrum, which outlines the variations in the universe's density across 3-dimensional space. In the universe's infancy, these fluctuations were minor, but as the universe grew, these variations in density became magnified. The scalar spectral index provides insight into the universe's origins by informing us how these initial fluctuations evolved over time. Using these 6 parameters, we can calculate not only the properties of the CMB, but also other cosmological measurements. For example, we can determine the universe's age to be 13.8 billion years, with a margin of error of 40 million years. The most restrictive observation comes from the CMB anisotropy, which are the subtle temperature variations. The standard cosmological model aligns well with all observations across various scientific disciplines, including physics and astronomy. One of the most important tools for studying the universe is the telescope. From early telescopes to modern ones, telescopes allow us to observe distant objects in space, from planets and stars to galaxies and nebulae. There are different types of telescopes designed to observe different wavelengths of light, from visible light to radio waves and even X-rays. Optical telescopes, like the famous Hubble Space Telescope, capture light in the visible spectrum, providing stunning images of distant galaxies and nebulae. Radio telescopes, like the Arecibo Observatory, detect radio waves emitted by celestial objects, helping us study phenomena like pulsars and black holes. X-ray telescopes, like the Chandra X-ray Observatory, observe high-energy events like supernovae and the regions around black holes. In addition to telescopes, scientists have launched numerous space missions. Space probes and satellites travel beyond Earth's atmosphere, providing a clearer view of the cosmos without the interference of our planet's atmosphere. For example, the Voyager probes, launched in the 1970s, have traveled beyond our solar system, sending back data about the outer planets and the interstellar medium. The New Horizons mission gave us our first close-up images of Pluto and continues to explore the Kuiper Belt. Moreover, the most advanced telescope, the James Webb Space Telescope, helps to study exoplanets and different celestial bodies. One of the key methods for studying the universe as a whole is examining the cosmic microwave background. The CMB is the afterglow of the Big Bang, a faint radiation that fills the entire universe and provides a picture of the cosmos when it was just 380,000 years old. By studying the CMB, scientists can learn about the early conditions of the universe, its composition, and its age. The Planck satellite provided the most detailed map of the CMB, revealing tiny fluctuations that tell us about the distribution of matter and energy in the early universe. Additionally, scientists conduct large-scale galaxy surveys. These surveys map the positions and properties of millions of galaxies, revealing the cosmic web, a vast network of galaxies and dark matter that stretches across the universe. The Sloan Digital Sky Survey is one of the most comprehensive galaxy surveys, mapping millions of galaxies and helping us understand the universe's large-scale structure, its expansion, and the distribution of dark matter. While observations provide data, theoretical models and simulations help scientists interpret that data and make predictions about the universe's behavior. There are theoretical models that are based on the laws of physics and are tested against observational evidence. Albert Einstein's theory of general relativity describes how gravity works on cosmic scales. It has been crucial for understanding the expansion of the universe, black holes, and the behavior of light in strong gravitational fields. The Big Bang theory is the leading explanation for the universe's origin. It describes how the universe expanded from an incredibly hot and dense state to its current form. Supercomputers are used to create detailed simulations of the universe's evolution, from the Big Bang to the present. These simulations help scientists study the formation of galaxies, the behavior of dark matter, and the effects of dark energy. Studying the entire universe is a monumental task that requires a combination of advanced technology, innovative theories, and international collaboration. Telescopes, both on Earth and in space, provide the data needed to observe the cosmos. Cosmological surveys map the large-scale structure of the universe, while theoretical models and simulations help interpret the data and make predictions.